Все.
Его составлю, я прямо у него. Да, пожалуйста. Не без проблем.
Так, когда вы разворачиваетесь,
Хорошо.
good morning, dear colleagues, one more time. And our today's first day of this week, we'll open our colleague from Science and Innovation Rosatom, Andrei Shadrin. Please, thank you.
Thank you. Morning, dear colleagues. Yeah, I am Andrei Shadrin. I'm working for Rosatom, I think, for 40 years, more than for 40 years, and mostly working about spent fuel management, rad waste management, and again, rad waste regarding spent fuel. I have a rather short presentation, so you will have an opportunity to ask me a question if it will be interesting for you. And of course, I will talk just about general question. What we plan to do now in Russian Federation, what we got, what is system, and how we understand now what is the situation with spent fuel will be next in the nearest future. Yes, it's presentation prepared on two and now one presentation for this year because the question is very interesting for Russian Federation as well. What we have right now. Now we believe what we should talk not about only third generation of reactor. We should talk about nuclear system, nuclear energy system, fourth generation. What it means? First of all, and it should have advanced safety. Right now we have a project in our world, different projects of reactors fourth generation with advanced safety, yes, but we also need this advanced safety for fuel cycle as well. It should have system high efficiency. It's understandable. If, to be honest, almost all what Rosatom and our company working in nuclear energy got money, it's just electricity. First of all, it's electricity. Yes, we have we have sale our reactor, we have sale fuel, but money for fuel, money for new reactor and our, anyway, we are going from electricity. So the system should have a higher efficiency, economic efficiency. Rad waste minimization, exactly. Of course, it's complicated question. Of course, when we are working with spent fuel, we couldn't say change amount of radionuclide. We just can wait, and short life nuclide will disappear. But we couldn't change nuclide components during reprocessing. we did not have any separation. So amount of waste, firstly, will be depends on spent fuel. It's easy to understand what all energy we have from fissile materials. And usually we talk about burn up. And what does it mean? It's mean how many heavy atom was fissioned during company in reactor. And of course, they separate for two fission products, and this fission product, rad waste. If we increase burn up of fuel, we increase amount of rad waste. We couldn't do anything with this one. Non-proliferation. I don't think what is really necessary to talk about why it's so important. And last one, it's unlimited resource base. Why it's important right now? Because for last 3-5 years there is an understanding what it's possible to move to non-carbon economy without nuclear energy. Yes, but it will be extremely expensive, and nuclear energy has a place in production of energy. Please pay attention what from I think in 2022 Europe mark investment in nuclear energy as green. So it's understanding not only for nuclear people, it's understanding for all world. Rad waste. It's very, very famous picture. You can find it, I think, in many sources. What does it mean? Of course, it's mean level of radioactivity on uranium ore. If we have no using of plutonium and no reprocessing, it will be going this way, and after 10 low than 1 million, about several hundreds thousands years, the activity of rad waste will be close to natural one. If we will have reprocessing, it could be drastically. We can drastically decrease a time when this equilibrium will be achieved. And as a result, if we will have this kind of system, we will not have accumulation of spent fuel. We will use of plutonium again, and you can see it's important to use a plutonium as well. We will use uranium-238 instead of uranium-235. And in principle, and we plan to do it, we can utilize minor actinides. What we will have as result? Closed nuclear fuel cycle with huge amount of sources, because we use uranium-238, and we will have environmental friendly system, because if we will just reprocess fuel and just use the plutonium for nuclear reactor for fresh fuel, in this case, a time of dangerous waste will be about 10,000 years. In principle, if we will able have partitioning and burn up minor actinides, burning of minor actinides, it will be about 300 years. You can see how we understand now ways of actinides in this kind of system. Probably we have two component. If a plant have two component system, more than that, right now Russian Federation really have two-component system. We have two fast reactor, BN 600 and BN 800, which working as commercial reactor. Of course, it's just two, and compare with I don't remember exactly how it's about 24 thermal reactor we got now. And we plan what, what spent fuel. Okay, we have cycle for thermal reactor and cycle for fast reactor. Spent fuel going to reprocessing, and after reprocessing, uranium will going back to thermal reactor, and plutonium, and will going to cycle of fast reactor for prepare fresh fuel. In principle, we plan what americium and the minor actinide as well will going here to fast reactor fuel cycle for transmutation and burning. However, there is some another possible way. For example, have liquid malt reactor for burn up, and it's under discussion. But for plutonium, it's exactly this way. And the fuel cycle of fast reactor will include transmutation of minor actinide. We plan what will separate minor actinide as well and put in a fresh fuel in this case. So for start, we have plutonium from thermal reactor, probably minor actinides as well from thermal reactor, and our fast reactor has oven fuel cycle. New system means new requirements, and we're trying, I think, 12, but maybe 12 years ago, we're trying to say what is the requirements we have for such kind of fuel cycle. First of all, it's imperative: safety, environmental friendly, and economy. And don't think so. It's really necessary to explain why it's necessary, why it's important, and technical. First of all, spent fuel for fast reactor in this system, maybe not for thermal reactor, but it's under discussion. We have reprocessed fuel with low cooling time and a high burn-up. High burn-up, it's understandable. We have increasing of burn-up for thermal reactor as well. It's about, right now, 6-7% of heavy atom. Approximately 10 megawatt is around 1% of heavy atom. For nuclear, for fast reactor, a burn-up is about 12-16% of heavy atom, so it's twice higher and compared with thermal reactor. And cooling time. Why it's important? It's easy to understand if you are thinking about huge amount of reactor. When we have just one fast one, two, maybe three fast reactor, it's not so important what is the cooling time we got. 5-7 years, that's okay. But if we will pay attention what any reactor for fresh fuel or any year, we put any reactor and take as spent fuel from reactor about 2 tons of plutonium. Maybe it's nothing. If the cooling time will be, for example, 5 years, it means from each reactor we will put 10 tons of plutonium in storage, and we will just keep in storage and pay money for storage as well. And maybe it's so not so drastic, but if it will be 100 reactor, fast reactor, it will be absolutely another figure, because it will be 10,000 tons of plutonium. It's a huge amount. I'm afraid it's absolutely impossible. So, for economy reason, we should have low cooling time. And of course, if you're working with spent fuel with low cooling time, we have a lot of radionuclides, short-living radionuclides, and it will be a lot of fuel has quite high temperature, and the processing will be not cheap. It's exactly will be expensive when reprocessing of thermoreactor fuel. So it means what we should find an optimum between amount of plutonium what we have in the storage and between the cost of reprocessing. Right now, we believe it's about 3-4 years for all of reactor cycle, for reprocessing and for preparation of fresh fuel. I think just practice will show we are right or no. Non-proliferation. Exactly, it's necessary. Losses of plutonium, neptunium, and americium in that waste, around 1.1%. Why it's 0.1%? Because with 3 years, sorry, with duration of hazardous waste, we will achieve only if we will recover 99.9% of plutonium, americium, and curium from fuel, and don't put it in a waste. If we will put it in a waste, we will decrease amount of hazardous of waste, but not so drastic. It will be about 10,000 years. Yes, products are suitable, should be suitable for fresh fuel. Yes, what it means? If we, or Russian Federation, we chose for fuel for fast reactor, two options. Main is nitride fuel, mixed uranium plutonium nitride, and another one is oxide, MOX uranium plutonium fuel. But China, for example, looking for metal fuel. If you have metal fuel, and we should product metal fuel, we will need another kind of reprocessing technology. Yes, in principle, it's possible use standard, for example, hydrometallurgy with Purex for metal fuel as well, but we will have different additional operation. Problems with dissolution, and our we will have nitrides or oxides, and should be prepare metal from this one. It will be, should be little bit expensive. So we should remember exactly what kind of fuel you got and what kind of fuel you will product. And the last one, very important, no liquid waste release in environment. What mean? We have right now just one example of reprocessing facility which is not on a seaside. And we use underground disposal for rad waste in this facility. It's Mayak facility near Chelyabinsk. All our reprocessing are situated on the seaside. And tritium, iodine, carbon-14 really going in ocean. Yeah. We suppose it's not a good way, and we should find a solution that we will not liquid waste in environmental. Situation in Russian Federation right now. Mayak facility, AT1, working from 1978, maybe 76, but probably 78. Capacity of facility is about 400 ton of spent fuel, but it was almost 50 years ago. And burn up our fuel was around 35 gigawatt, gigawatt per ton. Right now we are going to 70. And then I told you, when if we increase amount of, if we increase burn up, we increase amount of fission product, and we increase amount of plutonium in spent fuel as well. It's exactly, it's almost straight line. So for new fuel, Mayak facility couldn't reproduce 400,000 at all due to big amount of plutonium and big amount of fission product. So we really need have modernization of Mayak facility because we have a plan to reprocess MOX fuel of BN 800 at Mayak, and the plan started in 2028, I think, 29, in 2029. And the amount of plutonium in 1 ton of BN MOX fuel is about between 150 and 200 kilo, and compare with 10 kilo in spent fuel of thermal reactor. So capacity of plutonium line of Mayak facility should be increased. And we plan to do it exactly. Another one, it's mining chemical combine. Pilot demonstration center for spent fuel reprocessing, for reprocessing of VVR 1000 spent fuel. We got put in operation hot cell, first complex of PDC in 2016, and now in operation, and we test a lot of different elements of technology. And this year we complete construction of pilot demonstration center in Железногорск, and we will plan to have full capacity in 2028. Why it's so long? It's because technology of mining chemical combine has a lot of different innovation operation, which couldn't which wasn't used before in industrial scale. For example, volume oxidation of spent fuel, and we are afraid that we will shoot a lot of time before it will be pilot demonstration center will work for full capacity. The capacity is 200 tons per year. And the last one, it should just design. Right now, design should be complete in 2025. It's reprocessing facility for demonstration energy complex with reactor Brest. Brest is lead reactor with mixed uranium plutonium nitride fuel, and we propose use combine pyro plus hydro technology for reprocessing of this fuel in this plant. A capacity about 10,000 tons. Yeah, for IT1 and pilot demonstration center mining chemical combine, main technology is based on the Purex, it's hydrometallurgy technology. Different one, different kind of, but hydrometallurgy. What our plan in this future and why we really need it, not only because we have we start develop of fast reactors energy. Not only we need plutonium for fast reactor, but it's not one reason why we should modernize. Should have a modernization of AT1 and should put in operation pilot demonstration center. And also we need additional new plant around 1,000 ton per year, maybe two different model for 400, 500 ton per year. It's because the storage of fuel quite full. And if we will not reprocess, we will not stop accumulation of spent fuel. Of course, the biggest problem is to build a storage much cheaper and compare with build a facility for reprocessing. But if you will just storage fuel, forget about environmental and be ready to storage it for several 100,000 a year. It's requirements for technology for a new plant. There is not big difference on compare with main technology what I showed you before. I would like just to underline what is we plan to achieve. We believe what this one requirements should be achieved. What the problem is how to achieve, and now we will have R&D on this topic. First of all, no change in environment, including tritium. Tritium is a real big problem. I told you what the best solution right now for the world best. It's putting into ocean. Not good way. Personally, I believe what the best way just for tritium, not for another kind of radionuclide, it's underground disposal because it's just 11 years of half-life time. So we should control it just for 100 years. And Russian Federation has experience with exploitation of underground disposal for, I think, about 50 years. And we understand for tritium, it's good. It's not the problem. However, we should find any way to decrease amount of tritium waste anyway, because just we put fuel in water, we will mix water and tritium contain in tritium fuel, and we have huge amount of tritium containing waste. So it's really a problem. We should find what kind of partitioning we need. I think in 1918s, 17s, was a design of plant AT2. Almost all nuclides were separate for weighing oven fraction. It's possible, but it's really huge amount of equipment and it's very, very expensive. But if we will have no separation, we couldn't put americium, curium, and minor actinides in reactor. We should find what the deep of partitioning we need, how many fractions we should really separate from fuel, which kind of nuclide should be storage separately, which one should be storage together. It's really analytical task, and of course there is not a lot experimental data about this in the whole world, and we should find this problem. burn up, higher content of fissile materials, we solve this problem for reprocessing of breast fuel, but for 10,000 ton per year. And all approaches different and compare with plant of higher capacity. It should be really analyzed what we can use for big plant, what no. For example, not all decision from nuclear safety could be used for big site, big capacity. Because if you need just free or different, oh no, free same kind of equipment for 10,000, for 100,000, it will be 30, and for 400,000, 120. I think it's impossible from point of view. And so we should find a solution of this problem, and will be another equipment, maybe in our technology. I will, are you chemist? Yeah. Several words about problem, not about all. If somebody, if it will be interesting to can read this presentation, I would like just tell you what we have problem. High temperature tritium removal procedure. It's not easy. For nitride fuel, that's okay, because we totally destroy crystal of mixed uranium plutonium nitride. It becomes to oxide, no problem. Yeah, but if we just have oxidation of oxide fuel for uranium, should be good, because uranium UO2 becomes to U3O8, but plutonium does not oxidize and does not change the structure. So for MOX fuel with higher content of plutonium, it will be not so easy as for nitride, and it should be a problem. How to separate tritium from liquid rad waste? Anyway, biochemistry, hydrometallurgy, without water we will have no technology at all. Right now we haven't, not only in Russian, not only also in all world, we haven't analytical chemistry without water. Almost, maybe not almost all, but a lot of different analytical procedures based on water solution. In this case, we will have water containing tritium, and we will should find the solution for this problem. Isolation of minor actinide or transmutation. Yeah, it's possible to have transmutation of minor actinides, but
what's your favorite uranium? What is it?
But when you will stop reactor, it will take fuel from this one, we will should put it in another reactor if we use chromogenic. Reactor. So it will be necessary to find solution this one. For nitride fuel, we have task of management with carbon 14. It's not so drastic problem for reprocessing of nitride spent fuel, because it's easier to separate carbon 14, and we have not a lot of amount of carbon 12 in this fuel. But if you're talking about all kind of reactor where we use graphite as no construction, not only construction material, as neutron Okay, I think you understand. I forgot this English word. We have mixed of carbon 14 and carbon 12, and it's problem how to separate it and how to manage with this kind of waste. Maybe last one, we need find low temperature matrix for rad waste. Glass is good, but it's high temperature process, and a lot of nuclides, cesium for example, was going from glass during preparation, and we have a huge system of gas cleaning, and a lot of waste from this of gas cleaning, and this waste we should put back in head of process. It's possible, yes, but again, it's complicated and it's expensive. I would like to add what for radiochemical, for off reactor cycle, just last maybe 5 years we put attention for computer modeling. For reactor computer modeling using very well and for many years, but for radiochemical plants it's not so popular. We start to do something and can do something right now. For example, in university, Moscow University, there is a scientist who use quantum chemistry method for select extractants. For example, in project Prorыв, Bachwar Institute developed a computer called Wizard, virtual radiochemical plant, which can calculate mass balance of all facility, starting from cutting of fuel and finally all waste and all the technology. We can we can calculate cyclogram of equipment and trying to calculate cyclogram of working of whole plant. A lot of different models for optimization of production. We start to something for equipment, for example, for rad waste, for radiation and nuclear safety of any kind of equipment. We got a lot of codes, but we haven't it as a system. We should find how to, excuse me. And we should find a way how we should collect it jointly for system of development new equipment and development of new facility for design, firstly. And final several words about what we have right now. I told you about problem, what we should solve, yeah? But something we really able to do. And now we should find and put it in industrial, has industrial implementation of radiochemical technology for uranium, plutonium fuel cycle. For fabrication, we should find industrial technology for fabrication fuel with minor actinides. As example, BN 800 working in MOX fuel, and last year we put in BN 800 first I think it's just pins, several pins, which containing not only plutonium but also neptunium and americium. I think it's about 10 pins for reactor test. Hope everything will be well, and we will able, and we can start to put minor actinides in fuel for fast reactor. To achieve all our aims, we prepared and launched R&D program, new one. We trying use two commercial fuel products. This one we trying right now to find which kind of fuel cycle we need. Mainly it depends on how we should do with partitioning and rad waste, how it's minimized. And we will try to change something in our technologies to start and to have a more efficient, not so expensive plant. Finally, first step we done. BN800 working with MOX fuel, really with full zone, and plutonium for this fuel was taken from spent fuel of thermal reactor, from VVR. Yeah. Next step, it reprocessed fuel of BN800 and prepare fresh fuel from this plutonium. In this case, we will really close fuel cycle. I would like just add what reprocessing we got on Mayak facility and fuel fabrication in mining chemical combine in Zheleznogorsk. First assemblies from MOX assemblies from B1800 should be on Mayak facility in 2027, and I hope and I believe in 2029 we reprocess fuel, and in 2030 we'll put fresh assemblies from plutonium which we'll collect from BN800. Thank you. Thank you.
So much. Any questions?
I have several. First of all, when we're talking about the fast reactors, and today we have the sodium-cooled reactor, and the next step will be so enlarge the sodium-cooled reactor like BN1200, and then reactors with the lead coolant like BR1200. What is the main difference between these two types of reactor? Why we need lead coolant reactor instead of sodium coolant reactor?
Well, I would like to say what a final choice doesn't done right now. The first commercial reactor BN1000, first higher capacity commercial reactor will be BN1020 with potassium coolant. Yeah, with natrium. Yeah, with natrium. Sorry. Yeah, the different in safety. It's a lot of different things which for me difficult to explain for you. It's regards safety of reactor, but very understandable about safety of coolant. Yeah, if you have lead, it's not flammable. Firstly, and secondly, it's there is no leaking if you use lead. The temperature is about 360, I think, melting point of lead. And if you have leaking, it's just frost and nothing else. So we couldn't lose coolant, and you have one of type of heavy energy. And last one, yes, it couldn't be evaporate. too high temperature for evaporation. I think this one, but final decision will be made after Breast 300 will put in operation and will work with several years because the main problem with construction materials for lead. It's not easy choice and not very difficult task. I hope it will be solved.
Another question is about the time frame. You told us that next steps will be to take the plutonium from the BN800, make a new fuel, put it again to see how it works and what is the physical process. In ideal situation, what would be the time for all these operations? I mean, including the work of the fuel in the reactor, and reprocessing, make a new fuel, and burn it again.
Well, first of all, I would say that there is no any problem. It's mainly PR action. We know what nothing will happen if we will put plutonium from BN again for fresh fuel. Nothing will happen new. More than just PR. We take fuel from fast reactor and put it back in fast reactor. It's just PR, nothing technical reasons. So yes, I think it's done right now. We put fuel from thermal reactor to fast reactor and use fast reactor on commercial, I think 3 years. Probably yes. With full zone of reactor. When 800 start from mixed zone, it was about 12% of MOX fuel and all our was uranium fuel. But for last 3 years it's worked with full zone of MOX fuel. So nothing technical.
Okay, thank you. And the last question, what do you think about the final repository of the high-level waste? I mean, if we reprocess almost all the nuclear fuel, use almost all fissile materials, the volume of this high-level waste will be really small. Will we need the deep geological disposal, or will it be enough and just maybe subsurface storages or something like that?
Very complicated question. It depends on national rules. If we'll talk about Russian Federation, we have disposal underground. It's all kind of disposal, no lower than 100 meters deep. If it's more than 100 meters, it's deep geological disposal. So right now it's our rules. We have this situation. In this case, I can say yes, in principle, it's possible to have underground storage, but it will be around 100 meters exactly. But of course, volume of disposal will be not so drastic. It really depends on many factors, and right now, I think in 2025, Institute of safety. Yes, of Russian Academy of Atom should be Russian Academy of Science should find first stage of calculation which type of disposal and how many disposal we need for different kind of partitioning. Probably something will be interesting from their results and maybe something understandable.
Thank you.
Thank you.
More questions from?
I'm just curious because from your presentation you mentioned a lot of cost effect of this technology. So in average, how much this one facilities need to cover all the expenses, and is Russian Federation involved in like put an allocation per year for this kind of technology and things?
I'm afraid I couldn't give you a real answer. I just can show some estimation. Nobody tells how much they got from reprocessing of 1 ton of fuel. We can just estimate from different kind of sources, but it's around 2-3 thousand euro per kilo. Yeah. But when we are talking about new technologies, sometimes we can find in the literature estimation how it will cost. Low when 600 probably dollars, maybe no euro. I couldn't find in literature. So I think in reality we have a situation between 1,000 and maybe 3,000. How much it will be exactly? No idea. It's really commercial secret. And to be honest, I don't know how it. I really don't know what is the price for Russian in Russian Federation. No idea.
Okay, any more questions? If not, let's thank the speaker again.
Thank you.
Михаил Иванович, доброе утро. Если мы раньше начнем, удобно будет? Не в половину, а в 15 минут.
Анна, здравствуйте. Разрешите мне экран раздать?
Михаил Иванович, слышите меня, да?
Да, я вас слышу.
Ага, сейчас я вроде нажала разрешить.
Ага, сейчас попробую.
Попробуйте
Да,
еще.
все работает теперь.
Отлично, все, спасибо большое.
Так, я, наверное, появился или должен появиться.
Все отлично, видим вас и вашу
Очень
презентацию,
хорошо.
точнее.
Сейчас. Ага, хорошо. Ну, я тогда жду 11:15 и начну.
Mikhail, are you here?
Yes, I'm
Yes.
waiting to start.
So, colleagues, we are going to start right now. And Michael Ayjuvan is with us with his second lecture. Please start. Thank you.
Thank you, Anna. Thank you. Dear colleagues, good morning again now from my part. So we continue the lectures on a school, winter school on radiochemistry. So last week on Wednesday, Professor Petrov explained to you the essence and the classical methods of spent nuclear fuel reprocessing. And just before me, you were explained about the strategy of management of spent nuclear fuel in Russian Federation, where reprocessing is at the core of this approach, and where, by the way, by recovering, by using the fissile and not only fissile, but like uranium-238, the Russian engineers and scientists are, let's say, a step ahead. It's a quite advanced, actually, development in this area when we can burn really the uranium to a much deeper level and utilize the resources. So the nuclear power is sustainable really in this approach. Okay, so we are looking now what to do with the radioactive waste, which results from the reprocessing of spent nuclear fuel. So the content of my lecture is here again. I'm starting with the background. I will remind you several things that we already partly discussed, partly not. So some new things also will be introduced. And then we will look to the spent nuclear fuel reprocessing waste. And since they are solid and liquid, so my lecture is about solids and liquids. About the gases, you will have a separate lecture about the gaseous effluents. So liquid, solid and liquid radioactive waste resulting from reprocessing of spent nuclear fuel. So that's the content of the lecture. So I'm starting with another picture which represents the known already nuclear fuel cycle. This time it's coming from a report from United States of America. And it is again describing the main steps within the nuclear fuel cycle, the main steps. So again, things are starting with the mining, and you go to the fuel fabrication, and then in nuclear reactors we are burning partly the fuel, and then we have here the spent nuclear fuel. And with the spent nuclear fuel, we can go either to reprocessing, or if you consider that this fuel is waste, spent nuclear fuel waste, then we go through a stage of its conditioning. So it is put in some canisters, in some containers, and then goes to the deep geological disposal because it's high level waste, contains long-lived radionuclides, and activity is very, very high. So this is just a presentation again of the spent of the nuclear fuel cycle, and the purpose is to look to this part. So I'm returning to my picture. So that's the representation of nuclear fuel cycle, the picture, the schematic that I already used with you when I explained to you that we have got open nuclear fuel cycle with these arrows in blue color. So we are going through them to the disposal. But now, today, we are looking to the closed nuclear fuel cycle. So instead of considering the spent nuclear fuel as waste, is not anymore the waste, is a product that we are going to work with. So because of that, we are going to the reprocessing plant. And we reprocess the fuel, we recover useful materials. And most of the fuel is actually unburned. Only part of the fuel, it is burned, only a part of it is burned. And here, after the reprocessing, the recovered materials, which is basically uranium and plutonium, and the part of uranium and plutonium, they go to the fabrication of mixed oxide fuel. But we can use also just uranium to fabricate the standard for thermal reactors, for standard utilization like that one which is coming from mining. So the nuke fuel, which is again burnt, and etc. So my part is here. From the reprocessing of nuclear fuel, we are obtaining some radioactive waste. And this radioactive waste has to be processed and prepared for the future disposal. And this is the full picture that I represented to you. So we are in the closed nuclear fuel cycle, not open version. So we are looking to the red color arrows. So we are here in the reprocessing plant, and now the usefulness of my picture is that it shows the effluents which are considered radioactive waste or nuclear waste, because they contain radioactive elements, and the radiation is coming from nucleus, and because of that, radioactive waste, nuclear waste, they are synonymous. It's the same meaning, but nuclear, it's preferred, at least to me and to many, at least to me, because actually the nuclear reactions occur, and the radiation is coming from the reactions that occur in the nucleus. So it's nuclear waste. And what kind of the waste we obtain from reprocessing? It's, you see here, high-level waste, intermediate-level waste, low-level waste, and there are also some gaseous effluents that will be considered, that covered in the lecture on the processing of gas purification. We need to purify the off gases from all the processes, not only from here, from reprocessing plant, and then we have approaches how to do that. So my business is to look to liquid radioactive waste, solid radioactive waste, and to share with you the information about that. So you see here that this waste goes to immobilization and actually conditioning, because we put everything into the containers, and then they are directed to the disposal. And here it's the time to recall classification. It perhaps was somehow discussed. Many these issues you already heard many times. Nevertheless, let's look to the picture. So we have here the schematic of the classification scheme used everywhere in the world, but this is recommended by the International Atomic Energy Agency. So here is the level of activity content, can be concentration, but the total activity as well, vertically on this axis. And here is the half-life. So 30 years, including cesium-137, which is 30.2 years, the decay time, actually 30 years, 0.17 parts of the year is the half-life of cesium. It is still short-lived radionuclide by the definition of IAEA. So these are short-lived, these are long-lived, and then you have here the description of the radioactive waste, starting from which is considered as exempt waste, non-radioactive, although some radiation it is there, as everywhere we have radiation. So then we have very low level, intermediate level, and high level waste. Here, which is intended for deep geological disposal, because the decay times of this waste are so long, the times of the decay, that we cannot rely only on engineered barriers. And on the surface, during these very, very long times, many things can occur, and inevitably will occur, that will mobilize the radionuclides and is not safe to dispose of high-level radioactive waste somewhere on the surface. So they are intended for deep geological disposal. You have a lecture on that, so you will discuss more in details. So that part is actually the most difficult to deal with, and because of that is most attention. But once again, from reprocessing or spent nuclear fuel, we are obtaining all kinds of the waste. So low level, intermediate level, and high level waste. This waste is produced. And what is by definition? So in a document published by the IAEA, this is a safety guide. You see green color. These in the pyramid are going after the fundamental and then the requirements, and then you have guides. So this guide was published in 2009 by the IAEA, and it gives you the definition what is high-level radioactive waste or high-level waste. So you see that the levels high enough, radioactivity levels are high enough to generate significant quantities of heat due to the radioactive decay because of that, right? So these processes occur and they generate heat energy, which is deposited in materials, and then you have, as effect of absorption of radiation, we have heat, and the heat is enough high to take care of it. Or it is written in definition recommended by the IAEA, large amounts of long-lived activity, which needs to be considered in the design of disposal for this waste. Actinides, because the actinides typically are very long-lived with the half-lives of millions of years, like you take, this neptunium, americium, so resulting in the decay schemes of plutonium, of course. So actinides. If we speak about actinides, they are long-lived. And even the heat generation becomes low, but if the time of the total decays is millions of years, we need to consider in the design of repository, it means we need to go deep into deep geological formation where the conditions are stable and are predictable, the same, stable for ahead millions and millions of years. Okay, so disposal in deep, usually several hundred meters or more below the surface, stable geological formations is the generally recognized option for its long-term management. So this is where we are going to go to. And I put here the phrase about the management of the decay heat. And nowadays, in this document recommended by the agency, it says about several watts, only several watts per cubic meter, it's enough high to be considered in the design, but take care on that, because the previous IAEA documents contained mistakes, and it was another number which is wrong and could cause terrible catastrophes. So let's look to my country. This is the classification in the United Kingdom. So British classification scheme, you see very low level, low volume and high volume. In my lecture, not interesting. So low level waste, we have here the numbers. I don't have the slide on a Russian Federation because it presumably we covered in many lectures that you are obtaining from Russian experts. So then intermediate level waste, which this concentration of radionuclides exceed those for low level waste in United Kingdom, then this is intermediate level waste. And you see here in United Kingdom, and this is done in many countries, if also the heat generated and we need shielding, then this is high level waste. I added here the slide about the inventory, because about the inventory of the things in Russian Federation, again, you are provided by the expert from Russia. And this is from a paper published by my colleague from United Kingdom in Donald, very known specialist. He published monographs, many papers, overviews. So inevitable, if you work in this area of nuclear waste management, then you will see his papers, his monographs, his overviews that we are taking quotes from there. So in Donald, in glass technology, he put this table about the high level waste in 1995 in 1,000 cubic meters and expected in 2030 in United Kingdom. High level waste, and look here, that number was taken from IAEA from Vienna, and it was a terrible mistake. And he put here a quote, actually quoting me, because I was discussing with the IAEA to correct this mistake, which was a terrible mistake, which could cause, if you use this number, you see in intermediate level waste, if you'll approach 2 kilowatt per cubic meters, you can get meltdown. It is like in the core of reactors, everything will be melted and it's huge catastrophes. And nevertheless, in the old IAEA publication, it was present, this terrible mistake. So he indicated that this is a mistake. So intermediate level waste, you see here the numbers in 1,000 cubic meters, and low level waste. So all kind of, so that's United Kingdom Nuclear Waste Inventory, taken, published in Glass Technology Journal in 2007. And that was the prediction for 2030. This is the inventory as of 2024. So you see, it's much lower than the prediction here. Here is larger. Here is larger than the prediction intermediate level waste, and here is also lower than the prediction. So you can have imagination about the volumes of United Kingdom nuclear waste accumulated. And pay attention, because if you'll take by mistake somehow this 2 kilowatt per cubic meter, this can cause really a catastrophe if the volume of waste will be, let's say, 10 cubic meters only. Then you can get in big trouble due to the heat generation. So nowadays the IEA played back, you see, played down, and they put into the document several watts per cubic meter only. That's it. That's the limit. Okay, so we look to the classification, and the last about classification, it comes from United States of America. So you see here, they put here information about spent nuclear fuel, which also it is used in the United States as used nuclear fuel. Often the Americans, they in their publication use the word used fuel, not spent, used fuel, but these are synonymous, the same. So they defined that used fuel is fuel irradiated in a nuclear reactor that has not been reprocessed. So if it is not reprocessed, then in the United States, this is like nuclear waste. And when declared to be waste, spent nuclear fuel is generally assumed to be destined for disposal in a deep geological disposal. This is the so-called blue ribbon report of a commission that looked to Yucca Mountain disposal site and state. So it's available in the internet. So this is copy paste from this report, and I put it just to inform you about the definition of nuclear waste, spent nuclear fuel, which becomes waste in United States of America. So that was my introductory part, where classification plays an important role. So let's now move to the spent nuclear fuel reprocessing waste. So I put this picture to show to you. So this is fresh nuclear fuel before. So after manufacturing, you see here, typical, let's say, is 3% in thermal reactors, but can be a lot higher. It depends. If you take a research reactor, then can be maybe even 20%, the enrichment. But in power reactor now, the enrichment is not so high. So you have mainly uranium-238, 97%, and 3% typically. So it's not in stone. It depends. It depends on the reactor. So it's just a schematic to demonstrate you that after burning, after a couple of years, that the fuel was generating power, was producing electricity, was producing thermal power. The fuel is not anymore effectively giving its heat, its energy, and we take out the fuel, and now we call it used nuclear fuel or spent nuclear fuel. And this fuel, we have still 95% of uranium-238. It is still there. Only a part of it was transmuted and partly burned, producing electricity. And then you have here all kind of fission products. You see here 3% and 1% of uranium-235. It is still unburned. It is still there. And plutonium 1% in power reactors. And these are materials, at least uranium-235 and plutonium, that can be recovered and very effectively used and again in the nuclear fuel cycle. And this picture was not in this version, and another explained by Professor Petrov, and was present in the previous lecture, that this is spent fuel activity here. So no, this is radiotoxicity. So I'm using radiotoxicity to show how dangerous is the radioactive waste, radioactive material for environment, because radiotoxicity shows the total amount of water that potentially can be, potentially only, not really, contaminated by these radionuclides. So these numbers show that the volume that will be hugely increased to the volumes of Lake Michigan and huge lakes. And you had already examples from Kishtim catastrophe in 1957 from Professor Petrov. So that happened in reality after the nuclear catastrophes, right? So this is spent fuel. And if you are looking just to high-level waste, much faster just in about 1,000 years, the radiotoxicity becomes the same as of natural uranium. So we have great incentives, ecological, to keep the environmental clean, to reprocess the fuel. So that was said in my lecture and the previous lectures about that. So that picture was shown to you in my lecture last week about the reprocessing of nuclear fuel. Nowadays, 1/3 of the nuclear fuel, used nuclear fuel or spent nuclear fuel, is being reprocessed. So these materials are recovered and reused really. 2/3 of the fuel, it is considered as waste. Nobody is reprocessing this fuel. So the United States is not reprocessing the commercial fuel. They consider that this material, it's, financially, it is true. No reason to reprocess it, no big reason to reprocess it. And not only so, in Sweden and Finland and so many countries do the same. Because the fuel is cheaper to buy the fresh fuel and not to go into this technology, which is difficult to exploit. But if the prices will change on natural uranium, then of course the capacity of reprocessing plant will be increased, and this way will be not just 1/3. But nowadays you see the total amount of spent fuel, used fuel, approximately 400,000 tons, and 1/3 of it, so more than 100,000 tons, is being reprocessed. So in this picture, let's start with the right side. In the right side, I put a table. I put also here the links. So that is taken from Nuclear Energy Agency, and this is publication 2019. I don't have a more recent publication, and this is the same on the World Nuclear Association site, which was accessed in now. So that's August 2024. So very recently, right? And you see the table of the capacity of reprocessing of used nuclear fuel. So I'm in the table with you. And here you see who is the most powerful by country to reprocess the spent nuclear fuel or used nuclear fuel. You see the France in LAG, the capacity is 1,700 tons. Actually, the British were leading for a long time. United Kingdom, it's halted now that they're processing, but so both United Kingdom and France, they reprocess not just their fuel. They accept for reprocessing the foreign fuel, and after reprocessing, the vitrified high-level waste is returned to the country. And these countries are purchasing the fresh fuel, of course, but the high-level waste is returned to the country, is not accepted for disposal in the United Kingdom. By the way, United Kingdom, which is not advertised and not in the newspapers everywhere, but it was once published. In United Kingdom, for a certain amount of money, it is accepted to leave in the country low intermediate level waste, but it's costly. But if the country doesn't want to receive back this waste, pay the money, and the British will accept it for disposal. So, my message to you that, the general public is afraid, importing of the radioactive waste is a catastrophe for the nation. It's not a catastrophe. It's something that can bring, if you can't and you need the money. If you don't, of course, pay, and the job will be done by the foreign people. So France, then in Russian Federation, you just were informed about the capacity. I guess that this is a old number, 400 tons per year in Mayak reprocessing capacity. About the new things, you just were informed in the previous lecture, the capacity. And then you see here Japan, Rokasho, light water reactors mean LWR. So you see in total 2,100 tons per year. And then what other kinds of fuel? So let's say in Sellafield, this is metallic fuel, so from Magnox. But in reality, the British reprocess both oxide and metallic fuel. So it's not just this one with this capacity. Then India, you see here, and the total in the world. So for some of you, because many young people are here in the auditorium, but not only, maybe everybody is curious. it's not a bad here in Wikipedia. You see here the nuclear reprocessing. It's a good quote, and I access it just these days. And you have a much larger table, not only with the commercial sites, but also with military sites. Because first military started to reprocess the fuel because they needed plutonium-239 to make the weapons. So that there in the Wikipedia you can see other sites, but the capacity are not so high like here, so it's not commercial fuel. So I finished with the table. Now I move to, yes, I need to move a little bit faster, but look, here it's a picture that shows a MOX fuel assembly, but schematically they look similar. So when we are going to reprocess the fuel, we are dealing with this, like in this picture. So this is the assembly, which contain many fuel rods, depends on the design of reactor, but there are many rods inside. And then in the road, you have these capsules where you have actually the material which is fissiled, split in parts and gives energy. And all this bundle, all this assembly, so this is a MOX fuel assembly, but they look similar. It's going to be reprocessed. So somehow to extract from it, from this middle in a fuel rod, these tablets here, very small, that are typically oxide of uranium, oxide of plutonium, if it is a MOX fuel in this case. And they contain the materials that I just showed to you from the point of view of radionuclides, of course, but these are typically oxide materials. The bulk is oxide, difficult to dissolve, very durable materials like ceramics. Oxide fuel is a ceramic. You understand? It's a very durable ceramic, by the way. So this assembly is going to be reprocessed. And about the chemistry of reprocessing, you were informed by Professor Petrov. He showed you the schematic, the classical scheme of reprocessing. So these are chemical processes. This is a schematic, how this is done. So we have here typically in a pool. So under the water, we have these assemblies of used nuclear fuel, which is taken out of it. And because you saw these are entire constructions, it is called chopping. So we are cutting them into small pieces. So then they are dissolved. They are dissolved, and then you have these chemical processes that were explained to you, like Purex process was explained, Purex plutonium and uranium extraction. Purex process, standard classical process of doing all this chemistry and then extracting useful, recovering uranium and plutonium. So that is not my business of my lecture. My business is here. So what we obtain after doing all these kind of operations of reprocessing of spent nuclear fuel, we are obtaining some waste material, the material that is good for nothing. So it's waste, but it's radioactive waste. It's a lot of contamination, radiation there. In some parts, it's very, very high level of activity. And this is actually very high level of activity mainly here in the liquid. So it's written here, for the liquid storage in form of vitrified waste. But to get vitrified waste, you need to do many things. So I'll explain you what. And here it's cladding and related materials and the storage in containers. So these are basically solid and liquid radioactive waste. In this plant, there are some gaseous effluents. Once again, of gases will be covered in another lecture. I have lectures, by the way, I'm teaching to PhD students, Master of Science students, and I have a dedicated lecture on processing of gaseous waste. Even I published, when I worked for agency, a handbook on off-gas purification systems. So, but it's not my business. My business is solid waste and liquid waste. So let's start with the processing and mainly of solid high-level waste. But in reality, all kind of solid radioactive waste after, but the focus is on high-level waste because of the title is. But in here, there are not only high-level waste. So this is a table taken from an IAEA publication. And I explained to you that this assembly, it's a lot of materials there. It's not just uranium and plutonium there and fissile materials. And you see what kind of materials. So you have here in the table, zircaloy, alloy materials, which contain zirconium and other components, stainless steel, Inconel, and other alloy materials, special steel, and then from different type of reactors. So this is boiling water reactor from United States, from Federal Republic of Germany, pressurized water reactors. Let me see, it's not, but the Russians water reactors are the same like pressurized water reactors. So it's a version of pressurized water reactor. Inside of the vessel, of the reactor vessel, you have pressurized water. So it's water reactor is the same, like pressurized water reactors. And you see here some numbers. So it's in kilogram per ton of heavy metal, uranium or plutonium. So that gives you indication that there are many solid materials produced after the processing of nuclear or used nuclear fuel. Then this plot shows to you two things, and this thing is activity in Curie per tons of the fuel. It's just to give you the impression about and this one you cannot read, and I cannot read even from my screen, but the information is there about the content of radionuclides, about the level of activity, and here it's about the heat generated. So it's some heat generated per ton here, not per cubic meter, but nevertheless the level can be very high, and this is spent or used nuclear fuels still. It's not the radioactive waste, it's spent nuclear fuel. And light water reactor, the meaning, and pay attention to here. Here it is the burn up. How deep it is burned the fuel. So in the past, so this is an old publication that I took it. So some 30 years ago, how it was 33 gigawatt multiplied by day per tons of the fuel. Nowadays, we moved to other levels. So I have a slide where I will show you that. So what are these materials? On what the people are doing it in different countries? So this is from United States, site, Hanford, Savannah River, Idaho Falls. So what they do? They declad primary aluminum clad fuel, but some zirconium clad fuel. In West Valley, this is CHOP and leach cladding. This is a West Valley commercial fuel. So Hanford is also a military site, and Savannah River is a military site. So what they do with the solid radioactive waste? So you sell a field. So let's say you see here CHOP. So that's United Kingdom, and leach cladding, and then cementation. From 1990 till present, we do in United Kingdom use cementation, but not everywhere. In other places, it's not done the same. So in United Kingdom, and the photographs are taken from UK, but of course with simulants, and everywhere, not just in United Kingdom. So traditionally or generically, hulls and hardware, so all these materials, solid materials, have been managed together. And the most common approach everywhere to manage this waste is to wash, so partly decontaminate, and compact, or even without compaction, enclose in containers, with or without embedding in cements. So not necessarily, not everywhere cementation it is used. In some cases, in order to fill the gaps in between the solid materials, cementation is used, and we obtain inside of the drum, of the container, like this in this picture. So this is a cut section. So you see the solid materials embedded in a cementitious materials. This is a recent photograph that I took in a Kovra in Netherlands. So these are simulant canisters. So they are empty or filled with some simulant materials. So these are canisters for vitrified high-level waste. And this is exactly the same shape canister for this waste that I just showed to you. So this solid waste is put inside, without cementation, by the way, put inside of these canisters, and then stored in a Kovra facility with the name Habok in Netherlands. There are many options to deal with the solid radioactive waste, which is produced after, which is generated after a processing of. So it's a schematic that shows many options here. So it's taken from here, publication 1985, still valid. Still, all these options are at the level higher. Or I will show you one thing which goes to a quite high level. It is not yet available in IAEA publication. Will be perhaps soon, but not yet. At least is demonstrated at several IAEA technical meetings. This is a process which is produced by the so-called geomelt process, in situ vitrification or in container vitrification. So in situ vitrification, it is just directly on the site. Some electrodes are put around the place which is going to be vitrified. Electrical current is passing through this place and is obtained a block of vitrified product. Everything is melted together. In container or in container vitrification, ICV, it is when we do the same, let's say solid waste from the reactor, maybe even in a part after the extraction of the fuel, so active core, it is put into a container. Some additives are added here, some solid material, sand and other things. Electrodes are switched on and the material is vitrified. So solid waste in such way is transformed to a composite materials, and the fixing material is a glass. So it's vitrified. So this process is you see here the history of geomelt. I put for your information for additional reading, no time to go too deep here. So it is used in many places. This is my photograph, but some 10 years ago, so much younger. And this is my colleague who was the leader in the United Kingdom of in situ in container vitrification, Charles Scales. So we are here in Sellafield together, and it's here information. So it's experiments are done typically with simulants, and then we go to real application of this process. One more slide for your information. So this one, it is not yet used at the level to be recommended by IAEA in technical publication, but is already in technical meetings of the agency. The same for this one. Was done only with simulants. That was the work that I was the scientific leader in the Russian Federation when I worked some 20 years ago for an institution with the name Radon. So we developed, instead of electricity, we developed powder metal fuel. So we take the container, no electricity, because electricity should be megawatt power. So it's difficult, very really. So we put this powder metal fuel here in a borehole, shallow well. Then we close everything, ignite, and the fuel is melting everything down, and everything is transformed into a glass there, just with the power of thermochemical reactions. For your information, this is the reference. Who knows, you PhD students are here, just students. You can look to the reference and know, at least know for your information. Let's move to the liquid high-level waste. So the focus is high-level waste. Vitrification is the main technology which is nowadays used in order to process the liquid high-level waste after the processing of spent nuclear fuel everywhere. This is the main industrial process. Why? It is very attractive because the glass has the highest capability to immobilize the whole table of Mendeleev. All radionuclides can be immobilized in the glass. It is accepting everything. Simple production technology, which is adopted from glass production industry. Because to make a glass in reality is not so difficult. You take a sand, you add a little bit something there, you put in a furnace, obtain a melt, pour the melt, the glass is produced. That's it. Small volume of resulting waste form, so you decrease the volume. High chemical durability of glasses in natural waters. The next slide is about that. And high tolerance of glasses to the radiation damage. You know, radiation is amorphizing crystalline materials. So they are crystalline with regular distribution of atoms. If you account for radiation, if you have radiation, the radiation is shifting the atoms. And instead of regular crystalline lattice, you obtain an amorphous materials. What is an amorphous materials? It's a glass. And the glass also is affected by radiation, but it was amorphous and stay amorphous. Nothing changed with the glass. It is even a little bit improved. But of course, depends. If you go too high with radiation, radiation can then cut and burn everything. So about the durability of glasses, there are glasses taken from the bottom of ocean, so they stood for millions of the years in the salty water, which is extremely corrosive. And the glasses are still there with it's the level of you see here 300 million years, and only a fraction of millimeter is corroded. You imagine, so durable material in the nature. So these are natural glasses, and our borosilicate glasses are a little bit weaker, not so durable, but nevertheless very durable. And this is a recent glass which my colleagues from the Institute of Ore Deposits of Russian Academy of Sciences extracted from a volcanic caldera. The age of this glass is 145 millions of years, and is with uranium. It is so much uranium that can be considered even as a war. So it was irradiated by this decaying uranium there, and it is still there, and the uranium is still there. So it's really a very durable material, and this is silicate glass, of course. When we are looking to the high-level waste, which at the table you see it's very, very complex. It shows the chemical composition of the high-level waste generated in different countries. The purpose of looking on this table, but later you can look to the numbers and consider them. It is to show that the composition is really very complex. It's really very complex. It's difficult to deal with this radioactive waste because it's a very complex composition and contain all kind of, not just radioactivity, all kind of in oxide form, oxides of many elements from the Mendeleev table of elements. And this table is, as I promised to you, is the burn-up. So look here, nowadays we speak not about 33 gigawatt multiplied by days per ton. Typically now we move to 45 gigawatts multiplied by days per ton. So the energy which is extracted from the fuel. The burn-up is higher. We extract more energy in irradiating the fuel in nuclear reactors. So they work there longer. The burn-up is deeper. But the radiation, more fissile elements, the radiation is also higher. So of course there is a trend. There is a trend to move to higher burn-up to 60 gigawatt per day, but the radiation then it becomes even higher. So it's just to emphasize to you again this information. And you see here that then we are obtaining more fissile products, more radioactive rare earth elements, more radioactive actinides. So the high-level waste becomes even, let's say, more difficult to deal with from the point of view of radiation as well. When we reprocess the spent nuclear fuel, typically we obtain this number, 31 cubic meter of high-level waste in liquid form, typically. And they contain all kinds of these stable and radioactive isotopes, fission products. You see here all this forest of different, and of course, technological impurities, which by the content are even the major chemical components compared with radioactive components. And we vitrify this waste, and we obtain this canister. So from waste, which is produced on reprocessing 1 ton of spent nuclear fuel, we are obtaining 1.8 tons of aluminum phosphate glass like the Russians do in Mayak when they vitrify the waste. So it's 600 liters or 0.6 cubic meters. Or if you use borosilicate glass, the waste loading is better. So we obtain 150 liters only, 4 times smaller volume, or 0.4 tons of vitrified radioactive waste in canisters. That in Europe, they look like here. In the United States, they are larger, higher, taller. In Russia, they are smaller, but they are in one overpack. Here, it's also for the references are kept here. So about the glasses, sorry that I have no time to go, but there are stages of vitrification process and the definition of the glass given by Malcolm Faraday. Why the glass is so accepting everything? The glass is a solution of different elements one in another. It's like a solution, but it's a frozen solution. It is when you freeze the solution and obtain a solid material which contains the same content like at high temperature. So here it's just shows for sugar. At high temperature, we can dissolve in water a lot of sugar. But if you cool down, the sugar will precipitate and we will have crystalline sugar on the bottom of the can. But if we will freeze suddenly, then we will obtain the same concentration like at high temperature, but in solid form. In University of Sheffield that I am associated with, it is known in the world as a great school of glass. So actually the science of the glass was created by the Professor William Turner, who created a department to investigate the glass. So before Professor Turner, manufacture of the glass was an art rather than a science and technology. So then the British invented the flat glass production, all kinds of these things. So now we have, this is the building of University of Sheffield, the main headquarters, let's say. So there are many buildings. So this is my faculty, and this is from the Museum of Turner, because from the glass you can make tissue. And this is the costume of the wife for the wedding party, and it was made up of glass fibers. So he presented him on the wedding party, and that was a costume made out of glass fibers to wear. Imagine that. So glass is useful not just in technology; it's also useful in all our life and in art. Okay, so how the vitrification it is done? There are type of processes. The one it is adapted from the conventional industry of producing flat glass, all kind of bottles, all kind of the glasses. So we pass electrical current from a molten bath, and it keeps the high temperature here, and then we discharge the molten glass into the container canisters in here, or from the level in here, and that's how it happens. And this process it is used. This is a schematic of vitrification process in a Savannah. In Savannah River, in defense waste processing facilities, so Savannah River defense site. And this is the schematic of the whole process of vitrification, but the core of the process is actually that schematic that just was shown. So, so it is here. So the schematic is that one. So it's a molten bath with a certain volume where through this molten material, the electrical current it is passes, and because of that, it is called Joule heated ceramic melters, because the refractory here around are made out of ceramic. So their melter, in reality, a more true representation is this one. So it is shown here that they really have two options to discharge all the molten material from the furnace from the bottom drain or from the level. Typically this is done, and in order to facilitate the melting process, they also are using a kind of mixing, but mixing in Savannah River, it is done by bubbling. So the argon gas, it is pumped through this molten glass, and it assists mixing of the material and homogenization of the glass, homogenization of the molten glass, because the glass is only when this molten material it solidifies inside of the canisters. And you see here the parameters of they are using, so at least pay attention to the melting temperature. So Joule heated, so the electrical current which is passing through the molten material due to resistivity of this molten material, a part of energy of the current is absorbed here at the generating heat and keeps this temperature 100 to 1050 degrees. Then here are described other parts of this, so very briefly, very schematically. And that was one type of process. Another process, which is used industrially in my country, in United Kingdom, in Sellafield, but started to be used in France by the French. It is a so-called two-stage process. It is when before producing molten glass, the molten material here in the furnace, first it is done the process which is called calcination. Calcination means thermal decomposition of the salts. Because when we are looking to the composition of the high-level waste, I show you the table in oxide form, but in reality, because of the use of the nitric acid, these are basically nitrates, and we need to decompose the nitrates to transform them into oxides. And the calcination is doing this job. So this is a rotary furnace. It is a furnace which rotates and allows a better mixing inside, and is crashing because the denitrates are melted and they are glued to the sides of this rotating furnace, and the process goes very ineffectively. And here there is even a loose bar that is hitting the walls and destroying these layers that are glued inside of the calciner. So this is called calciner. So by doing that, so this is the temperature is not so high to melt the oxides, but is enough high to melt the nitrates and to decompose them into, transforming them into the gaseous, so oxides of nitrogen. If the carbonides are decomposed, then oxides of carbon. So the off gases are coming here for purification, and mainly in oxide form, these materials are then poured into the melter. This is the melter, where the temperature you can observe, it is like in the previous 100 to 1050 degrees. And in order to produce a good glass, here good, it means durable glass that is durable now and durable in the future. Then some glass frit is added, some already glass particles that being mixed with this calcine are melted together, and they produce another molten material, which is then after a certain time, it needs, let's say, residence time about 1 hour at least to be here to get a good homogeneous composition material, molten material. It is discharged into the canister. In the canister, molten material solidifies and transforms into a solid material, which is called glass. This is the glass. So in a better representation, it is shown here. So it's again a complex system. So you have the feed tank where you have a high level radioactive waste, and because this is here high concentration of components, it's even mixing by using a propeller here. So keep mixing all times this high level waste solution. Then it goes to the calciner, and here in the calciner some additives are used as well. And one of the additives is, by the way, sugar. In Russia it is called melassa. Sugar, it is added there, which is organic material, right? But it allows to decrease significantly the volatilization of gases here in this apparatus, the sugar. So it keeps reducing atmosphere in the calciner, and it is used industrially. It is used in Russia. It is used in the one-stage process, by the way. Here it's a two-stage process. In the United States, it is used in France. It is used in the United Kingdom. I know the parameters from UK, of course, rather than from other countries. And then we have the melter, and then we discharge from the melter into the canister, and then we have this. So in Europe, the United States, the canisters are made up of stainless steel, and the glass is poured. It's not just once, so several times the molten material is poured into the canister, and then we obtain such canisters filled with high-level radioactive waste. Of course, that the photograph is a simulant, it's an empty canister, there's nothing there. And because of that, we can safely take the photographs. So that was taken in Netherlands, where they demonstrate to visitors how safely they store the vitrified high-level waste, which partly was received back from United Kingdom, by the way. So the fuel from Netherlands was reprocessed in United Kingdom, and the high-level vitrified radioactive waste, it is under this floor, which is very, very, very thick. It's more than 1 meter thickness. And there, deep underground, so it's after the shielding, we have the real canisters. And above, just simulants to show the things. So this is the table that shows the vitrified high-level waste in the world from this publication. So you see that the leaders, let's say, or the countries that industrially use this process. So France, two vitrification plants. So it's in La Hague, two plants, R7 and P7. The years of operations that I could collect the data to show you. So 8,252 tons reported to 2019. And this is the immobilized radioactivity in terabecquerels. Then you see here United States, in Savannah River, in West Valley for commercial, in Hanford, that's military site, Hanford. So that's their main sites where they use. And by the way, in Hanford, they are today, this year started with simulants, but they are putting into operation the largest in the world vitrification plant for low-level waste. It is actually intermediate level waste, but in the United States it goes under the label low-level waste. So it's a huge by capacity low-level waste from Hanford site is going to be vitrified, the whole amount of the waste to transform it into a glass. And by the way, in container vitrification, they also use therefore solid waste in Hanford. So you see then Russia Federation, the reported figures here. Then United Kingdom and Sellafield reported numbers to 2012. Sorry, I'm from UK, but I could not find more fresh data to report and to put in the table. Then Pamela operated. That was a joint project together with Germans in Europe and Japan here. Sorry. No, this is another Germany. In Karlsruhe, they finished. They had for their own, they vitrified the total amount of a small party of reprocessed fuel in Karlsruhe, so that they vitrified it, and it's not anymore operating. So it's completed the campaign. And in India, three sites, and from one of them, you see 28 tons of vitrified. Maybe we have here some participants from India, but I am in contact with the experts that work in this area, and I could not receive more fresh information about other sites from Tarapur and from Trombay. Here you can look to the composition of the glasses. What kind of glasses are being used? Practically everywhere are used borosilicate glasses, apart from, you see here, Belgium. So here it's silica, so silicon dioxide. And you see everywhere apart from two places. Here it is no. Instead of it is oxide of phosphorus. So phosphate glass was used in a Belgium-Germany project in Pamela. So for a certain amount of time, not for all. And then they switched to borosilicate glasses. Everywhere apart from Russia, you see Russia, it is using phosphate glasses. All other countries, they are using, you see, the main glass forming oxide, it is silica, silicon dioxide. It is the main. So silicate glasses, borosilicate glasses are being used everywhere, which are known from the nature that are for millions of years, even with uranium, they are still there. The rate, the leaching rate or the rate of corrosion are extremely small. So fraction of millimeter per millions, per 100 millions of years. So really very low corrosion rate. I put here for your distraction, let's say the glasses are colored by the presence of certain elements. So that is for your distraction. That is why the glass is used in art, let's say. So we can color the glasses in different colors that are very nice. The nuclear glasses are, all of them, they are black. So it's not these colors. But look here. This is a representation, this is a photograph of a mosaic, which was manufactured by the famous, you are in the university named after Mikhail Lomonosov. The Lomonosov Moscow State University is named after Mikhail Lomonosov. Mikhail Lomonosov is a very well-known, worldwide known scientist, and he worked with glasses. He was interested in developing different colors for the glass, which then, and he designed and manufactured and tested about 3,000 sorts of glasses. to select those that were good to manufacture this mosaic, which represented the Poltava battle a very long time ago. It was a battle, and here it's this mosaic. It's available not in Moscow, it's available in St. Petersburg in the museum, but the university is named after him, a known chemist, so natural scientist that work also with glasses, for your information. If we are looking to these black glasses, not so nice, not colored, nuclear-based glasses that are radioactive, so it's not good to look at them at all. But simulants are normal to work with, so we can look to them and so on. And if you look into the microscope, it's a typical photograph. So they contain a lot of crystalline phases inside. So I'm a glass scientist, and I would call this material a glass composite material rather than the glass. It's not a homogeneous glass. It is not that glass that some of you may be aware and looking through, which is very homogeneous, or window glass, where the content of crystalline materials, it's much, much lower than a fraction of percent. So it's really very, very, very low. In nuclear-based glasses, you have many crystalline phases embedded in a body of the glass. Here it's a scanning electron microscope photograph that show that they contain many crystalline phases. So that's actually the glass in the photograph. And then you see here different spinel particles, zirconium, rare earth particles, and so on. This is the reference from where I took. But if you look to any glass taken, so recently the Russians published a paper where they took a core sample from a vitrified radioactive waste from Mayak that was manufactured long time ago, maybe 30 years ago. So the publication just appeared in the press. So they looked, and the content is something exceeding even 20%, the content of crystalline phases in the, and the same is everywhere. Don't think that this is just, but I mean the advantage of Russian, though I worked myself personally with my colleagues, not just myself, we worked with simulants, which we were provided by the BNFL, National Nuclear Laboratory nowadays in Sellafield. They provided University of Sheffield with samples of simulant glasses that were produced on the line, of vitrified line, when they started operation. But they started, as usually ever is done, with so-called cold tests, when instead of radioactivity, we use everything which is simulating. And then we manufacture these materials that are simulants. So cold tests manufactured glasses that one-to-one the same like radioactive glasses, but without any radioactivity. So I know that these glasses contain a lot. We published the data, so a lot of it's picture like similar, not like, but similar to that one that I'm showing to you. In the body of the glass, there are many crystalline phases, and this is typical for vitrified radioactive waste. So that's important information that perhaps it's good for you to take to have it with you. Now it's the last slide of my today's lecture. It shows you the cover of available in the internet report published by the National Academy of Sciences of the United States of America. It's comparison of waste forms. So that means all kinds of the materials that are immobilizing the radioactive waste. So including glasses. So waste form technology and performance. So it contains the information about bitumen, which in some countries it is still used. About cements. Cements are used everywhere in all countries as a waste form. So this is the basic material for low and intermediate level waste everywhere, in all the countries. This is the basic material. Cements are also used, as I already informed you, for solid radioactive waste, which can be considered as high level waste when these hulls, these materials resulting from cutting of bundles of assemblies of nuclear fuel. After washing, we obtain these solid materials. And in UK, we put this material addition into the cement. So cements are used everywhere. And glasses are used as a main material to immobilize high-level waste, as a main material. They are used for solid waste, for higher level of radioactivity when in situ vitrification, in container vitrification is being used, and many applications are already available in the United States, in United Kingdom. It was a couple of slides taken from IAEA reports that I demonstrated to you. So glasses are also covered here, and the usefulness of this reference is that contained also test protocols, information about test protocols that are being used in order to characterize the material. Because if you in your research, you want to develop something, you want to investigate something, you need to use standard test protocols to be able to compare your results with other results. So it's a good reference to be used. So it's available in the internet. And I took it here and I put it here a little bit advertising it. I'm not co-author, but it's a good reference indeed. I put here some references, so let's say I'm advertising my publications, but I put here because of this plot. This plot shows the trend, nowadays trend in developing waste forms for high-level waste. So in this triangle, it is, let's say here in this corner are absolutely homogeneous glasses, like optical glasses that we are wearing, window glasses. So it's just glass, no crystalline materials. And this corner, we have crystalline materials, but very durable ones, like in thin rock, So perovskite, hollandite, the phases that are immobilizing, zirconolite, they are actinides and fission products, and they contain in a crystalline lattice, and the thin rock is more durable compared with the glass. At least nowadays, after radiation, when it will amorphize, will be the same like the glass. But until it is not amorphized, it is much more durable compared with the glass. So in this corner. But we know that there are many crystalline materials. Crystalline, but durability, it's not good at all. So take table salt, take sugar, so take nitrates of sodium, of cesium, and so on. They dissolve immediately into the water. So they are not durable. And when we manufacture ceramics, the danger always it is that along with durable crystals, we will obtain non-durable. So in reality, our materials will be somewhere, maybe here. They can contain all the phases: durable crystals, non-durable crystals, and glasses. And of course, the trend is to work along this line. So to work with durable materials, with durable glasses, and with durable crystals. And the trend is to use glass composite materials, to use waste forms which contain both glasses, which are very universal, very tolerable. They accept all kind of, instead of making non-durable crystals, let's make glasses durable, which will dissolve these components, and we will not get to this undesired part of the plot. So the trend is to stay somewhere here rather than keeping the job just here or just here. And once again, when in the recent publication from Russian scientists, they analyzed the vitrified phosphate glass, this real produced in Mayak. They are here. They are not here. About 20% of material is crystalline in the body of the glass. When we published our papers in Sheffield, University of Sheffield, from samples from Sellafield, we also found that a lot of crystalline phases are in the body. So the reality is that with the vitrified radioactive waste, we are here. It's a glass composite material rather than a real glass. So we say glass, nuclear glass, vitrified waste, and scientifically this is a glass composite material, and there are some publications that you can refer to. So that's it. In reality, 2 slides. So that one is conclusions. So solid radioactive waste, low intermediate waste is produced, resulting from spent nuclear fuel processing, is encased in containers, and usually, not always, usually embedded in cementitious materials. So not all of them. In many cases, it is just in containers. Liquid high-level waste from spent fuel reprocessing is vitrified, producing durable either borosilicate or phosphate glasses, which provide a reliable mobilization of radionuclides and a high degree of environment protection. So that is the conclusion of my lecture. And the very real slide is that one, and which I thank you for being with me all this time. And I put here two informative materials I added. So the first one, it's there are here at least two students from India. So welcome to the School on Radiochemistry, dear Indian colleagues that decided to stay with your profession in nuclear area. In Kolkata, in the city of Kolkata, in January, it is held the 27th International Congress on Glass. And this Congress is held every 3 years. And it has a dedicated part for nuclear waste vitrification, because the glass, it's really very useful material used industrially for almost 50 years in the world. So it's a long history of utilization of the glass in making safe transportation, storage, and disposal of nuclear waste, high-level waste, the most dangerous waste that we are dealing with. So that is that one, and I put here because this is one of you. There are 12 symposia in this Congress, so mine is S6. I'm the chair of the symposia, and of course that we will have reports given by scientists coming from different countries, from Russia, of course, from United Kingdom, from United States, from France, from around the world to report about the achievements, including nuclear waste, application of glass for nuclear waste immobilization. And that one, a recent one, because there are students here and PhD students, and soon you will look for a work placement. Pay attention, because I'm collaborating with the King Fahd University of Petroleum and Minerals in Saudi Arabia. And they recently, last year, they created a center which is industrial nuclear energy center, interdisciplinary research center, led by Professor Shams. I am collaborating with him. And this is an announcement. There are vacancies there. And by the way, there are vacancies to apply for a PhD, but PhD are not interested. So for postdoc, you will finish your PhD work. You will look for postdoc application to do more science. And you can meet one day me even there. And here you see they are looking for engineers, and they decided to develop nuclear, and it's an opportunity for you. So the information it's here in the slide. You can copy the email of Professor Shams and then contact him for interest, or via me then to get there. So dear colleagues, thank you. With this, I'm finishing my lecture, and you are invited to discuss this.
Thank you very much.
I'm stopping sharing.
Colleagues, maybe some questions?
Thank you very much for this lecture. I have two questions. The first one, you mentioned about the locals in those countries where reprocessing plants exist to be against the reprocessing of other countries. Could you probably give any examples how this problem was solved?
You know, specifically, I don't know that the population was against reprocessing itself. I know that the people that are not aware what's happening with the environment and with us humans, they are generically against nuclear. So their perception of nuclear maybe started because of nuclear weapons. I don't know. They do not accept anything nuclear, even not realizing that some medical procedures and diagnosis and treatment are also nuclear. So so they reject anything nuclear, but what they hear about? They hear about nuclear power plants. Oh, nuclear energy, nuclear power plant is very dangerous. Let's close it. And I'm sorry, the things happened in Germany, a very well-developed nation, but they decided officially, and this happened in Sweden, officially to not go anymore nuclear. Things changed, and now it's more for nuclear than against nuclear. So things changed. But sorry, maybe you can again explain me if I misunderstood you. But it's such that rejection is of everything nuclear, not just reprocessing. As for reprocessing, but you'll correct me if I'm not answering to your question. As for reprocessing, then reprocessing, it is the case of nuclear applications first. And these reprocessing units for reprocessing of irradiated fuel to extract basically plutonium-239 to make weapons. You know how the military works. Everything is secret, everything is closed, and nobody even have the possibility to say something against. So typically the population is not involved in such things and reprocessing. As for reprocessing on a large scale of commercial, let's say commercial, so then it's the case that like the table that I showed to you. So these are very developed countries. So Japan, India, France, United Kingdom, Russian Federation, United States stopped commercial. So the West Valley, that was commercial fuel because of mainly economical reasons for them, not because of population is against of that. But in relation to the question that you ask about, in these countries, somehow it happened that more or less the public is more developed and not so much against of nuclear. And maybe the last example is for Japan, because in 2011, you know, Fukushima happened, and of course that everybody was absolutely scared. Nobody was even injured from nuclear by the artifacts of this tsunami and explosions of this, because the personnel evacuated from there and so on and so on. But radiation, of course, a strong belt, and everybody was very scared. But consequences were mainly because of some psychological maybe things. But I mean, in Japan, it is still no significant general movements against utilization of nuclear power. They still accept the nuclear power. So sorry, maybe something more certain you want to ask me, but if the ways to convince the public how to deal with that, it's to be open. I recently visited Netherlands. I visited Netherlands, a small European country, something like 15 million people. I can't remember exactly, but so it's a very small country. And they are, most of the countries, even below the sea level, right? They use nuclear power. Population is with nuclear power, but their radioactive storage facility, I show photograph with the canister from there. The part which is for low-level waste and intermediate-level waste, it is kept so clean with the so good conditions inside that the museum, national museums from the country, they are bringing their historical things that they want to store safely and in good conditions, not to be aged, there, together with radioactive waste. At the moment, for free, they are accepted to keep their some pictures, some rags that have historical importance to be kept. And the conditions are so good, but what means historical? It means that the population can get to the storage site, applying in advance, of course, visit this site, walking through, Here are the canisters with the waste, not closer because the radiation is higher. Here are the historic artifacts. You see, they are safe here. We are keeping together with the waste in order not to be aged. So it's a fantastic example of how to interact with population. They see everything, and because of that, some of them, of course, are against. You never can convince 100% of the people, but the main voice is for those people that are, they have the facts in their hands and they see the proofs that really things are safe. So my impression is that openness, it is the main playing card in convincing the population that we are doing everything safe.
Thank you. Yeah, you answered my question. And one more question about the structure of glass. So you showed a table that most of countries use silicon oxide, and in Belgium and Russia it's phosphorus oxide, but I didn't catch your idea why.
The reason of using phosphate glasses was that the composition of the waste is such that phosphate glasses were better accepting to dissolve all the components and to fix them in the glass structure. So when this technology was developed, the borosilicate glasses, because that happened long time ago. So historically, the decision was in favor of phosphate glasses based on the composition of the waste, high-level waste itself. And this time, and this was not a problem for Western high-level waste, but was a problem to dissolve in a borosilicate glasses for the Russians at that time when things started to be developed. And the phosphate glasses are not, they are a little bit weaker compared with the borosilicate glasses from the point of view of corrosion rate, these things, but not much. They are still providing all necessary parameters for retention of radionuclides. And because of that, historically, the Russians, they developed next and next melter, keeping the same glass composition. In about year 2000, it was a decision and was announced at international conferences that the Russians are changing to borosilicate glasses. So that was announced in about 2000 year. It was announced by the Russian scientists, not by me. I was present at conferences when they declared no more phosphate glass, we go to borosilicate. We have composition that accept our commercial waste and so on. But things happen in such a way that they still keep the pace with the phosphate glasses, and to my knowledge, they are not going to switch to borosilicate glasses. But the phosphate glasses are not, let's say, much worse, so that no good to use them. I'm not saying that. I know the glass well. The Belgium and Germans in Pamela, they used phosphate glasses only for a short period of time. But to work with phosphate glasses, it is also not something pleasant to do. The point is that if you take phosphate glass, in order to have it, you are working with phosphate acid. And then you have, hot phosphate acid. And then everything is corroding and it's destroyed. So it's something that there were serious reasons for the Western scientists and engineers to move away from the phosphates because it was difficult to operate with this glass. So meeting these problems, they decided to stay with silicates. Silicates are better compared with phosphates because, look, in the nature, we have, the silicates minerals. We have silicate glasses. So we have something very, very solid to show now in relation with your previous question. So look, in the nature, we have the glass, which is there for 145 millions. The uranium, it is still there. It is inside. It decayed there. Nothing was leached out of that and so on. So then the general public, it's something that we can believe too. So from this point of view, it's better to use silicates because we have examples from the nature. And I'm telling you this, I'm convinced, but so on. But we cannot foresee everything. Very often we have surprises from the nature, surprises from science. We are so convinced that these things are working, and And then, Einstein was wrong, because 3 years ago, it was awarded Nobel Prize for instantaneous communication for entangled quantum particles. Things that Einstein and Podolsky and Rosen published 70 or 80 years ago, that this is wrong for quantum mechanics, and so on.
Thank you.
Thank you so much. Any more questions? No. Okay, Mikhail, thank you. We appreciate you for your lecture.
Thank you.
And now, please don't forget your lunch tickets and have a nice meal.
что мне всегда не хватает авторитетов рядом, на кого можно сослаться, кому можно эстафетную палочку передать, валить, да. Отлично. Colleagues, friends, are you in? Everybody is here? Or should we wait a couple of minutes more? No? I see to the big boss. So when he make a sign, I will start.
Okay, colleagues, please take. Everyone already taken their seats. So today we have our great colleague from the Tenex, Rosatom, Mikhail. Please, you can.
The floor is mine. Okay. Good afternoon, everybody. My name is Mikhail Baryshnikov, and today I would like to talk to you about closing of the nuclear fuel cycle. And since you are the radiochemistry students, it could be a high rank motivation for you and for your future job, because I would like to show you how the radiochemistry and your specialty could be useful for the big power and big money nuclear industry. So we have 75 minutes for the task, and to fulfill this task successfully, I would like to disclaim 3 simple rules which will help us to do it better. First is, I'm not a professional professor. That's why I will probably get lost and forget something, and that's why I will use my papers, and please forgive me for this. I think that, well, if you agree with it, I will do my best to talk as interesting as it possible, and with pictures, by the way. The second rule is, let's respect to each other and to your neighbors. And if there is suddenly a necessity to go out, please do it quietly. Don't ask attention to yourselves. And if when you come back, do it quietly as well. And third rule is, if you have any questions, please memorize them. Please write them down, because at the end of the lecture, it will be a special time, 15 to 20 minutes, and I will try to answer all the questions that you have. And I also provide you with the email address in my contacts also at the end of the presentation, and you will write me at any time you have any questions. And I will also try to answer your question as well. If it is okay for you, we can start. I guess that everybody is here, and we will not be looked to the door. So, as you may know, all the good speakers starts their presentations with showing that the speaker is the same as the audience, the same roots, the same interests. And in my case, it is quite easy, because at the different stages of my career, I placed different places, and I started as the academician scientist, research scientist in Kurchatov Institute. Then I worked as a businessman. Then I was invited to be a high-level administrator in Rosatom. And now my position is somewhere between these 3 points, between scientists, between administrators, and between businessmen. So I guess that you as well could find yourself and your future position somewhere in this triangle between businessmen, researchers, and administrators. And it means that we are on the same floor and we are speaking the same language. And if so, the language started with the definitions. So it is not the canonical definitions. You can find in IAEA glossary in other words, but the meaning, the sense should be the same, and it is just simplification made by myself to understand you what are we talking about. And it is very important because, well, it's our language. So if you miss something during my explanation of this list, or maybe you don't see something of it, anything from this slide, don't forget, because don't be afraid of, because I will repeat it several times during my presentation, but we should start with this list, and let's do it. So First of all, nuclear fuel. Usually it is uranium and plutonium, but from the point of sustainability, from the point of the, well, correct attitude to this material and to this substance, it's better to consider nuclear fuel as the ready-to-use manufacturing, not device, but, well, matter. So nuclear fuel, in my understanding, is not just fissile material, but also claddings, also spacer grids, and so on. Then what else? Uranium mining. It is all the operations related to the uranium extraction from the ground and up to the yellow cake. So the final products here is yellow cake. Fabrication of the nuclear fuel. It is all the operations for making uranium cake into the mechanical products, into the fuel assembly. In case when you, so it includes, it covers all the operations that you, well known when you read or listen to the fuel cycle. So it is uranium mining. So it's after uranium mining and making the yellow cake, it is conversion to hexyl fluoride uranium, then enrichment of uranium, then reconversion, and finally making the pellets, assembling the fuel rods and fuel assemblies. And if you use just the natural uranium as the fuel, like in Cantu fuel, for example, there is no enrichment. If you use as a fuel any mixture like MOX fuel, for example, there is no enrichment as well, but you have a mixture there, alignment of the powder. But in any case, fuel fabrication is everything from the yellow cake to the final mechanical product for the fuel assemblies. Then irradiation of the nuclear fuel. This process, when nuclear fuel really works in the reactor with splitting of uranium and plutonium nucleus and release of energy, a huge amount of energy, and the most important part of the nuclear fuel cycle, of the nuclear fuel life, because all the requirements for the fresh fuel are determined by the irradiation conditions. And all the characteristics of the spent fuel are also determined by irradiation conditions as well. So the next one is light water reactor. The most popular type reactors as for now. So this is the base of nuclear fleet all around the world. And it will be the base of the fleet in the foreseeable future, at least until 2050, but I guess that's much more. And it's clear why, because the main matter there, the reflector and the coolant there is water, and mankind knows what to do with water, knows how to press it, how to boil it, how to clean it, and so on and so forth. That's why this is the most popular reactor. And when I'm talking today about the nuclear fuel cycle and fuel characteristics, I will refer to this light water reactor first of all. Then spent nuclear fuel is the nuclear fuel after irradiation. Sometimes we call that spent nuclear fuel, it is the matter then that no longer usable in its present form because of depletion of the fissile materials, because of the poisoning, and so on and so forth. But it's not 100% right, because there are some cases when we use spent nuclear fuel again. Maybe you know about the case of Leningradskaya nuclear power plant, for example, because right now, at this moment, we use the fuel which unloaded from the closed nuclear reactor in the reactor which is not closed yet, which is still under operation. So we use spent nuclear fuel again. That's why this definition is not so bright, but when we call it nuclear fuel after radiation, it's quite good. So let's call it so. And it's very important to note that spent nuclear fuel, in fact, is completely different substance than the fresh nuclear fuel, because it has different characteristics, it has different, well, parameters, and the only thing that is similar to fresh nuclear fuel is the size. So the size is almost the same, but everything else is quite different. Then, reprocessing of the spent nuclear fuel. It's clear cutting a dissolution of the spent nuclear fuel with further partitioning of the high-level waste and recovering of uranium and plutonium, other valuable elements, and solidification, or, well, let it be vitrification of the remaining waste to be finally disposed, finally entombed. Very important part is radioactive waste. It is material for which no further use is foreseen. It is important because in some countries where there is no plan for reprocessing of the used spent nuclear fuel and recycling of fissile materials, spent nuclear fuel could be considered as a waste. And contrary, the countries which plan to do it, which already reprocess spent nuclear fuel, they could decrease the amount of radioactive waste which is sent finally to the final disposal. Because americium could be the nice example. If you usually it is considered as a waste, it's clear, and the usual way is to vitrify it and send to the final disposal. But if you use it in the fuel of the fast Newton reactor, for example, it is valuable. It becomes valuable. If you use it for generation of the plutonium-238, for example, it's also available. So in this case, this material could be not the waste, but could be available. And well, another example also concerned to americium is amount of americium now, for example, in Russia is very big, and some of it could be useful, would be used for the further application. Some other part could not be used. So the first part will be useful material, valuable material. The other will be remaining will be radioactive waste. What else? Nuclear fuel cycle. No, it's clear the whole life of the nuclear fuel from its cradle to the grave, or if we are talking about recycling, from the cradle through the irradiation to reprocessing and recycling, and well, the whole life of the fuel. Front end is a part of the nuclear fuel cycle, all stages of the nuclear fuel cycle, starting from mining and up to manufacturing of the fuel assemblies. Back end is another part of the nuclear fuel cycle, starting from the cooling, unloading of the fuel, spent fuel from reactor, cooling in reactor pool, and finally either encapsulation and entombment or reprocessing and recycling. And sustainability, the key term of my today's presentation, is formally it is about financial stability, about rational consumption, about international cooperation, and so on and so forth. So in simple words, it is about all the good things, about all the right things. But we will talk about it in more details later. So now I would like to finish this slide with the thesis that after exploration of this list, after understanding of what is it, the only task that we have is just to find the relation between these components, between these terms, and it will be the task of our today's lecture. So finally, we hope we have to link all these words to each other. So, doesn't work. Could you help me? Good. So let's look to the chart and repeat the definitions from the previous slide. I like this picture much more than others because you can find very many illustrations of the nuclear fuel cycle. I like this one because of the right accents that we can see here, and due to this nice guy with the pointer which points these accents and say the right words. So what do we see here? First of all, it is mining, and it is illustrated with this lorry. And do you see the number? It is about 50,000 tons of uranium ore, which we use for further fabrication of the fuel. So next you see the conversion to uranium hexafluoride. After conversion, we have enrichment of this material. After enrichment, we go to fabrication of the fuel. And after fabrication, well, the fuel assembly goes to reactor. So this part of the fuel cycle is called as front end. And then we have light water reactor and irradiation of the fuel in this fuel reactor. And this is the central point of the fuel cycle. You can see that the guy shows to this object and say electricity, because electricity is, well, the aim of all our activities. And you can compare the numbers. From 50,000 tons of uranium ore, we produce 7 billion kilowatt hours. So it means that, well, the activity was, so the fuel fabrication was to be made. Then what we can see further, it is storage of the spent fuel in the reactor pool or at the pool away of reactor, and final disposal of the high-level waste. So this is the back end of the nuclear fuel cycle. And well, finally, you can also remember this this number is 27, right? Yeah, 27 ton of spent nuclear fuel from 1 gigawatt power reactor. If you remember the previous slide, so there are no watts, reprocessing, and sustainability illustrated by this picture, because this fuel cycle is open, and it is impossible to illustrate these two terms with this picture. But we will talk about it later for sure. And now, once again, let's repeat the definitions with the real pictures. This is the, this is uranium ore, this is yellow cake, and altogether they're about mining. Then we have pellets, uranium dioxide pellets. This is also the pellets, it is the real size of it. Fuel rods and fuel assemblies, one type, another type, and one more type. So altogether it is the front end. Altogether these pictures are fabrication of the fuel, and altogether these pictures are front end. And front end ends with the loading of the fuel assemblies into a reactor. And well, we could talk about it for a long time, because it's very interesting. All the stages and all the pictures could be described for hours, I guess. But today we have a little bit different objectives. But if you have any questions concerning these pictures, these stages of the nuclear fuel cycle, you can ask me at the end of the lecture. And now let's go further. And well, it is not easy to illustrate fuel irradiation in the reactor. It's, if you remember, it's the central part of the fuel cycle and the most important part of the fuel cycle. But the conditions of irradiation in the reactor are very terrific, because there is the high temperature, there is a huge pressure, there is irradiation by gamma and neutron, there is internal swelling, and so on and so forth. And absolutely no chance to make any photos. And the only one you can make is just before the irradiation starts. So this picture is made just before the vessel is covered and irradiation started. And instead of the different pictures and different illustration of the irradiation, I put here the challenges, the main challenges that irradiation presents to the fuel. It's also very important because it's real modern trends. You can catch from the nuclear industry and from the nuclear fuel cycle practice. First of all, the main trend today in this market, in this field, is increasing duration of the fuel campaign. It means it corresponds to the increased enrichment of the fresh fuel by uranium-235, increased burnup up to 70 megawatts. It is today's data. I guess that in 10 years it will be even higher. Another interesting trend is reactive power maneuvering. So electricity grids ask to the nuclear power plants to be flexible and to follow the loading, electricity loading, and it means for the fuel increased requirements for the fuel stability, both for fuel and cladding. Another trend is accident persistence. Very famous type of the fuel today is accident tolerant fuel, ATF, maybe you know. It is fashionable, even fashionable, because the main companies who promote this fuel are Framatome and Westinghouse. And they know a lot about advertising, they know how to do it. So now everybody are talking about ATF. Another two bullets are repairing capability of the fuel assembly and plutonium involvement. In both cases, we have to get the special construction, the special design of the fuel assembly, which could be repaired remotely, which could be manufactured remotely. So finally, we get these characteristics as well. So what else? So we have to remember all these characteristics or all these trends when we are talking about nuclear fuel cycle, when we are talking about sustainability of the nuclear fuel cycle, because, well, this is the real condition of the fuel on the market. Well, do you remember the definition of the spent nuclear fuel from my slide? Okay, I will help you. Completely different substance. What are the difference? First of all, the properties. I told about it, so that this is absolutely different from the fresh nuclear fuel. And what kind of difference? What are the main dangerous characteristics of the spent nuclear fuel? Do you know? Could you help me? You're welcome. Sorry? Heat release, right? What else? Any others? Fission products, but well, it is internal characteristics. Let's call it so. But when we are talking about external characteristics, about well, how to measure the ones which we could measure, that is heat release absolutely, and another very important characteristics is well, radiotoxicity or radioactivity, and you can feel this difference. You can feel the importance of this difference by these pictures. So if somebody could tell me what is the main characteristics of all these devices, or what is the common characteristics of all these devices which I illustrated by the pictures, you're welcome. So, any ideas? Protection, right? The thickness of the walls. So you can see here different models of the casks, for example, this one, this one, this one. So all of them are the casks for fuel storage and transportation. And you can see that all of them are very strong and very, very heavy. So it means that it is about safety. So we know how to protect this fuel, how to protect people from this material, and it also means that backend is not so terrific, because sometimes people are afraid of it, and sometimes people are even against nuclear, because the nuclear waste or spent nuclear fuel seems to be very dangerous. But well, we can be sure that it is a routine job for nuclear industry. Nuclear industry knows how to deal with it, how to treat this material, and how to pack it and transfer from one point to another point. And sustainability, the key point, the key word, key term of my presentation. Here I would like to refer to United Nations Sustainable Development Goals. Does anybody know what is it? What are the Sustainable Development Goals by UN? Okay, so this is the general aims, general goals, which were formulated and fixed by United Nations in 2015 as a universal call to to end poverty, to protect the planet, and to ensure that by 2030, all the people in the world enjoy peace and prosperity. And there are 17 goals. And yeah, it's clear that like any other general goals, they are formulated in very common words. But understanding the spirit of this document and using the key words, you can easily get the certain requirements for the nuclear fuel cycle from these goals. And sorry? Absolutely, absolutely. Yeah, and you can see, well, it's too small, but well, you can find easily it's SDG, the abbreviation of these goals, anywhere in Wikipedia, on UN site, and somewhere else. So once again, what could we derive from these goals concerning the spent nuclear fuel, which concerning the nuclear fuel cycle? Sorry, what are the main characteristics nuclear fuel cycle has to have to be called as sustainable? Well, first of all, minimize the volume of radioactive waste. So it's more or less clear. We have to think about our environment. We have to minimize the danger influence, the danger impact of our activities. The next one is reduce the danger life of radioactivity waste. So the less waste, the less level of danger is better. Another one is implement fuel recycling. So it's about rational consumption. So the less we get from the nature, the better. And then create sustainable partnership. It is first of all about international cooperation, about friendship, and so on, and ensure non-proliferation of critical nuclear materials. So it is also more or less clear, and well, we also have to do it. So at least these requirements should be met to say that our solution, our nuclear fuel cycle, is sustainable. And all of them, not just one or two, all of them should be covered if it is possible. Could we call this kind of nuclear fuel cycle as sustainable? What do you think? What are your versions? Absolutely right. No, because all the spent nuclear fuel here is considered as the waste. So nothing else. All the danger, all the heat release and the radiotoxicity of the fuel sent to final disposal to the final repository. And the danger, danger life of this waste is up to 1 million years. So could you imagine what is 1 million years? It's absolutely, how to say, maybe we could theoretically assure that it's possible, but only theoretically. Nobody could give you a guarantee that in 1 million years we can get this or that. So next is no recycling. There is the direct indication in the United Nations goals that we should think about rational consumption and think about reusing of material. There is no international cooperation, no fissile materials underground. I mean, no cooperation concerning the final disposal of spent nuclear fuel. But it's clear that we could cooperate, and industry is cooperated in the front end of this type of fuel cycle. But when we are talking about final disposal, about entombment of spent nuclear fuel, there is no cooperation at all. Maybe some advices to each other, but nothing else, because this is responsibility of the country which owns the spent nuclear fuel. Well, and all the fissile materials goes to underground, so if there is a need, it could be recovered, and the nuclear bomb is still possible. But the good news is we know how to close the nuclear fuel cycle, and there are some examples. And this example is taken from France. It is French nuclear fuel cycle illustrated. And you can see here that we don't send the spent nuclear fuel here directly for final disposal, but first it goes to reprocessing plant, and recovered uranium goes further for enrichment and fabrication of the fresh fuel. Plutonium goes for the mixture with depleted uranium and making MOX fuel. So both uranium and plutonium, the main fissile materials, could be reused with this scheme. And the only thing which goes to the waste, which is not used, it is all the remaining except uranium and plutonium. So it's much better than just the open fuel cycle, but it has still a problem. The problem is called MOX spent nuclear fuel. It is not so much, just 12% or even less from the whole nuclear fuel cycle, which is generated in France. But the danger of this material is much higher, because there is plutonium after radiation in a light water reactor. Well, it has to be cooled at least 30 years in the water pool or even more, and that's why one more reason. The plutonium after light water reactor becomes, well, not good. There are very many even isotopes in the whole composition of plutonium, and that's why it could not be used again in light water reactors. And that's why MOX spent nuclear fuel in France is near to be considered as the waste, and it has to be also sent for final disposal, unless they have fast neutron reactors, but they don't have. That's why MOX spent nuclear fuel is a great headache for them. And only after that, we could not call one through nuclear fuel cycle, or the French model of the nuclear fuel cycle, as sustainable. It is closed, but not sustainable. Another problem is considered to the minor actinides, which are not recovered from the used nuclear fuel here during pre-processing and goes to the final disposal. And the time of danger, let's call it so, period of danger, is up to 300,000 years. So it's also not so good. Well, now we understand more or less what is the problem, and I propose you to relax a little bit. Here you can see the QR code, and behind the QR code you can find the question. The question and three variants of answer. Please choose the one you consider right, and we will see was I clear and convinced or not. And well, there are three questions. So one by one, I guess 5 minutes is enough for this. If you are finished, just show me the sign. Raise your hand. If it goes well, all the questions dedicated to the information that I've shared with you. So if you remember my words and my slides, you can easily find the answer. Right answer. You can find answer in any way, I think. Girls, is it okay? Great. 3 questions, yeah. 2, 3. Well, at least half of you completed the test. Yeah, great. So let's go further. This is one. Well, first question, the next question. Huh? No, the questions are on your side. So I don't know if you are right or not, but well, you can cassettes later in the break, and if you still have the same question for me, I can answer it. But well, I think it's not so difficult. Well, let's go further, and to understand how to improve the French recipe, how to improve the model of the nuclear fuel cycle, which was illustrated before, it is necessary to understand what is the essence of the spent nuclear fuel. Here on the slides, you can see the results, because this slide is taken from the Rosatom presentation when we present the results. But in our case, we have to understand first why. We have to understand the reason. The only conclusion that I would like you to get from this slide is that every fraction goes its own way. So for every fraction, we have different, for all the fractions, we have different solution. It means that partitioning of the spent nuclear fuel, partitioning of the high-level waste is absolutely necessary. And well, so the question is, well, being a student of the radiochemistry school, if I ask you about what is the main danger generated by the spent nuclear fuel elements, by the content, I think that you will answer with this, that it's americium, neptunium, curium, cesium, strontium, plutonium a little bit. But when we are talking about sustainability, the question is different. The question is what to do with all these fractions, what to do with all these elements to minimize the danger, to decrease the volume of waste, and so on and so far. So let's start with the most exciting part of the spent nuclear fuel, which is labeled with yellow. It is minor actinides. Copyright to the slide belongs to Moscow State University Chemical Faculty. So first of all, thank you very much for this material, which is, by the way, open, and yeah, you can find it in internet easily. So this is the illustration how the radiotoxicity of the different components of the spent nuclear fuel decreases by time. And radiotoxicity here is an illustration of the radioactive danger of the spent nuclear fuel. Here you can see this total curve, right? So here you can see the case when spent nuclear fuel as it is. So without any reprocessing, without any partitioning, just fuel as it has. And you can see, please remember the form of the curve, because the next case is when we remove plutonium from the fuel, from the spent nuclear fuel. You can see that there is a difference, but in general, it's not so big. So the curve is a little bit smoother, but well, it's still danger. The next stage is when we remove americium as well. And you can see that situation is much better. The curve is much steeper. And finally, we also remove neptunium. And well, finally, it is much, much better. So the activity of the fuel, or the toxicity of the fuel, drastically decrease in about less than 1,000 years from the start, from the beginning. Well, the conclusion to this exercise is following. If we remove minor actinides from the spent nuclear fuel, its danger decrease drastically in hundreds of years. This is the same exercise, almost the same picture, but with certain named examples. You can see here the first curve when it is also radiotoxicity, and it's also the time. And this is the radiotoxicity of the spent nuclear fuel without reprocessing. So you can see, and this red line is activity of the uranium ore. So you can see that activity or danger of the fuel, because of the spent nuclear fuel, became equal to activity of uranium core is in how many? It's about 300. Oh, sorry, it's about 1 million, right? Close to 1 million. And this is the real case. This is Yucca Mountain in the United States. So they would like to not reprocess used nuclear fuel and send it for the repository as it is. And yeah, not only United States, but also Germany, Finland, Sweden, Canada. They also decided not to reprocess used nuclear fuel, and they go this way. The next case we already mentioned, it's French case, LAG reprocessing plant. And here we remove uranium and plutonium, but everything else remains in the waste. And you can see here that the time when remaining, radioactive waste activity became the same as uranium ore is about 300,000 years. And this is our Russian case. When we remove not only uranium, plutonium, but also minor actinides. And what we have finally, it's about 300 years for time of danger. And well, you can see that different interesting numbers here, but I would like to point your attention to the conclusion. Conclusion here is if we find a way, if we find an application or understand what to do with the minor actinides, it is, well, acceptance of the nuclear power, acceptance of the radioactive waste which is generated by nuclear industry will be much better. And well, it could be recipe for our sustainable nuclear fuel cycle. So once again, about minor actinides, partitioning and transmutation. There are four simple theses on the slide. If you can read them, it's very good, but I will repeat it briefly. So first of all, it's the minor actinides, neptunium, uridium, and curium, is the most dangerous part of the nuclear fuel, spent nuclear fuel, after 300 years of storage. Do you know what is the most dangerous part of the spent nuclear fuel in the first 300 years? Are there any ideas? Cesium and strontium, right. Well, the next thesis is we could split it. We could decrease its activity by transmutation of these elements into the most stable elements. It could be made by neutron or proton. And since we are in Russia operating fast neutron reactors, big scale, commercial fast neutron reactors, for us it's easier to use fast neutron reactors for transmutation of neptunium, uridium, and well, curium as well, but curium could be just stored and transmitted to plutonium by itself. And in fact, we already started this program. We already started transmutation of the minor actinides this year, 2024. The first few assemblies with adding of americium and neptunium were loaded into the core of BN800 reactors. So transmutation is started. And the fourth thesis is that it is confirmed that with homogeneous addition of just 3% of minor actinides to the fuel of fast neutron reactors, you can burn up to 70 kilos of minor actinides per year in fast neutron reactors. And this number corresponds to the spent nuclear fuel of 3 light water reactors. So you can see that in this case, fast neutron reactors could be, how to say, a solution for this problem. So let's talk a little bit about fast neutron reactors, which is our magic wand. As I said you before, we in Russia have 2 operational units of fast neutron reactors. One is BN600, another is 800. Another one, the third one, BN1200, is already under construction, and it will be in operation, I guess, in 2032, 2033. But we also construct the lead-cooled breast reactor, and we also construct molten salt MOSART reactor and some other apparatus. So Russia develops fast neutron reactors, And for all of these reactors, for all of these apparatus, the same feature is absence of a moderator inside the reactor. So it means that the average velocity, the average speed of neutrons there in the reactor is much higher than in light water reactors. And it opens for us the new capabilities for concerning the working with the elements, with the components of the spent nuclear fuel. And what else? And first of them, first of our new possibility is minor actinides. I already said about it. Another one is plutonium, because for plutonium, it's interesting that for fast neutron reactors, it doesn't matter what is the isotopic composition of plutonium. So it can work with any plutonium which is loaded to the fuel core, and we could use it, and we already use it. So the fuel for BN800 is manufactured from MOX, from mixture of plutonium and depleted uranium, and there is 20% of plutonium inside the fuel, and full core, 100% of the core is loaded with this fuel. And you can compare it to the French situation. We started our presentation with the French model. They also use MOX, but in French MOX, there is just 9% of plutonium in the fuel, and only 30% of the core could be loaded with plutonium. Well, let's go further. This is how to implement plutonium in the nuclear fuel cycle. Please forgive me that the picture is made not in the same manner that you're used to see with this nice guy who is pointed to the certain points. But these pictures are also notable, at least for me, because on the left you can see the picture which I made by myself in 2017, and I presented it at some conferences. And in a year, I saw this picture in Chinese presentation. When first they showed it as international experience or international models, international impressions of the future fuel cycle. But in some years, they changed the picture, you can see at the right side, and they add their Chinese pictures of Chinese facilities, and even Chinese terms and Chinese names of the main components. And this picture is in Russian. It's taken from the Rosatom review concerning the Chinese consideration about the future development. So my picture came back to me from China as a Chinese recipe for the plutonium involvement in the nuclear fuel cycle. And an idea is very simple. So if we could not use plutonium in light water reactor because, well, isotopic composition becomes worse, let's use it in fast neutron reactors. And after usage of the plutonium in fast neutron reactors, we get better plutonium than before. And we could use it again in light water reactors. So a kind of, how to say, infinity sign you can find here. And well, in fact, we already mastered just the red plutonium curves. The blue plutonium curve is to be coming soon. So we're going this way, and Chinese as well go after us. And well, you can see at the picture also the plutonium roots, uranium curves concerning the reprocessed uranium. And I'm happy to say that concerning uranium, we mastered all the curves, and we know how to work with reprocessed uranium very good. I would say that Russia has very nice experience of using reprocessed uranium in our own Russian reactors. You can see some words about it here on the slide. I would like just to point that in previous years, all our RBMK type reactors were fueled with the reprocessed uranium based fuel. And we had 11 units of RBMK, 1 gigawatt power each. So you can imagine 11 gigawatts of electricity produced by the reprocessed uranium, by uranium which is taken from the spent nuclear fuel. And well, we also have an experience of using this material in VVR, and Unit 2 of COLA NPP is loaded with this fuel right now for many years already. And it was also a big scale unit VVR which was loaded with processed uranium. It was on Kalininskaya NPP. And now Rosatom goes into direction of loading of all PVR 1200s by the reprocessed uranium fuel. So it's everything clear with uranium recycling, and we understand how to do it. Some words about short-lived fraction. As you correctly said to me, this is the fraction which is the most danger in the first 300 years of spent nuclear fuel storages. And well, as for now, we consider it as the waste. In fact, we use some strontium and some cesium for, well, heat sources or gamma radiation sources. But the request for this material is not so big, it's not so strong. That's why the most part of strontium and cesium became the waste. And if so, we have to understand how to ensure the safety of this material for a long time. And you can see here a description of the main technologies that we use. First is vitrification, you can see it. Then encapsulation, and finally entombment, borehole entombment, as it is. It's international term for this type of technology. Well, what else? Well, the else is a couple of words about infrastructure. If you remember the picture when I illustrated the back end of the nuclear fuel cycle, there were very many casks, very many models of casks. But in fact, for a sustainable nuclear fuel cycle, only two types of casks are enough. First is transfer cask, which is used for unloading the used nuclear fuel from the reactor pool. And another one, and for transportation as well. And another one is the bigger one for temporary storage and transportation as well. And this one, yeah, we already, how to say, designed these casks and manufacture this one of the casks. This cask will come next year, as I remember. And it could be also used for final disposal of the short-lived fraction, not just for used nuclear fuel, but for high-level waste as well. And altogether, these two types of casks cover all needs of the nuclear power plant operator or the owner of the spent nuclear fuel concerning the transportation, temporary storage, and, well, even final isolation of the spent nuclear fuel and high-level waste. Well, since you are the students of radiochemistry school, I think this picture is much favorable for you. That's why I would like to say to show you that for almost last. Unfortunately, it is in Russian, but the students again, there are no surprise for you because it's Purex, classical Purex, and I can just remind you about the main stages of this Purex. First is receiving and sorting. And this is technological scheme of the Russian radiochemistry plant RT1 in Ozersk. So the first stage is clean. It's receiving and sorting of spent nuclear fuel assemblies, then cutting and dissolution in nitric acid, then extraction of uranium and plutonium from solution, uranium affinage, plutonium affinage, radioactive waste treatment. And, well, then we go further and already implemented another components, which are also based on the same technology, but note what are the fractions that we work with. Neptunium. Neptunium extraction and purification is also implemented at this plant, and another one, americium, curium, cesium, and strontium extraction as well. I will not tell you about the certain technologies because I know that you have the special speakers for this and the real professionals from the, how to say, this industry. So I would like just to point that reprocessing is absolutely necessary for sustainability. And we have to separate from the spent fuel at least these several fractions: uranium, plutonium, minor actinides, cesium, and strontium. On the commercial basis, we have to do it in commercial basis. Let's try now to combine all the components that I described above. This is the picture from the Rosatom booth at Atom Expo 12/19, 5 years ago. And here you can see all the stages of the nuclear fuel cycle, which we touched today. The first is light water reactor. You can see. Then the spent nuclear fuel from reactor put into the casks. Cask goes to reprocessing plant, and you can see stage by stage the process, the technology of reprocessing. So it is fuel storage, then cutting, then dissolution. What else? Extraction, and what is the right name? Solvent extraction as well. Filtration and extraction. And what else? Then we have uranium and plutonium routes, well, curves, the routes, okay. And it goes for fabrication of the new fuel. Then we have irradiation of the plutonium fuel in fast reactors, and reprocessed uranium fuel goes to light water reactor. What else? Then we have partitioning of the high-level waste. And here we get a long-lived fraction, which is minor actinides, americium, neptunium, curium, which is as well goes to the fast neutron reactor. And finally, the remaining part is short-lived fraction, cesium and strontium, which is vitrified, put into the casks, and goes to the customer, to the owner of the nuclear power plant operator. So the cycle is closed. Amounts of and danger of waste is minimal, and the fuel cycle is sustainable. Right? Applause, applause. So we could get this. But not yet. Why? Because we have to consider sustainable partnership. If you remember my explanation, my translation of the UN Sustainable Goals, one of the bullets was international partnership. So it means that our solution has to be attractive for the customers, has to be commercial. And finally, we've done it as well. You can see here the 4 components. So we gather together all the technologies into the several blocks. We call them components. And you can see the first one, the first component is long-term storage systems. So it means casks and transportation system. The next block, the next component is spent nuclear fuel reprocessing with high-level waste partitioning. Then uranium plutonium fuel fabrication and, well, using again, and minor actinides burning in fast reactors. So altogether, they make the commercial product, which we call. Do you have any ideas how? Well, sustainable nuclear fuel cycle. So we are not original. We use the right words for the right products, and well, this is a real commercial product that we offer to the markets. And once again, this is 4 blocks or 4 components of this product. And you can see, you can read what are included into these components, into this product. And what does it mean? It means that at every bullet, we could indicate, we could put the certain number, the certain price. I don't like to show you now the certain price, commercial price, but just believe me that we understand all the how to say all the prices, all the cost of these bullets, and it means that the price could be transparent for the customer. So everything is clear, everything could be calculated, and up to the minor actinides, starting from the unloading of the fuel from reactor and up to the final points, final steps in radioactive waste conditioning, we understand everything. So it means that for the customer, everything is clear and could be calculated easily. And another confirmation of the clearance, the real picture from the real sites, from the Russian facilities, is it's interesting that all this picture belongs at the same time to the front end and to the back end, or contrary, doesn't belong to the front end and to the back end. And for example, you can see, you can imagine reprocessed uranium. It is recovered from the spent nuclear fuel. That's why, by the definition, it has to belong to the front, to the back end. But at the same time, it is used for fabrication of the new fuel. And that's why it belongs to the front end. That's why, concerning our new ideas, concerning our product, concerning sustainability, I'm always wondering when officers in IAEA or WNA, they split all the activities concerning the fuel cycle into the front end and back end. It was clear in former time when we didn't have fast reactors, for example. But now it is, how to say, it's not clear, it's not rational, because we are not about front end and back end. We are about the fuel cycle, the whole fuel cycle. And in our case, we are about sustainable nuclear fuel cycle. And now, one more thing about sustainability. You know already the picture on the left, and maybe you know the picture on the right. If you ever visited Brussels or Luxembourg, the headquarters of European Commission, you will absolutely see this picture, because this is the illustration of the circular economy. Well, let's call it the main approach of the whole European policy concerning the whole activities that Europe supports. It means that nevertheless, where are you from which industry, what you are doing, what are your products, you have to follow this way. You have to think in this way, and you have to master your processes in this way. And you can see that even the geometrical form of the pictures are similar. Here you can see the entrance to the cycle, and here is the entrance to the cycle. Here you can see the small exit, let's call it so, with a small amount of material from the cycle, and then you see the circle. So it means that from the social point of view, our solution, I mean, closing of the nuclear fuel cycle, is the only possible way, is the only recipe that could be realized. So we consider nuclear fuel cycle the only appropriate model when it's closed, and fissile materials recycling is also here in this recipe. Well, I see that you're a little bit tired, so let's make another quiz again. So you can also find the questions behind the QR code, and it is again based, all the questions based on the information that I've already told. And Anna, you proposed to show the final result, right? This time, let's do it. Let's try to see what is the. Sorry. Yeah, second quiz. Okay, we could see the first as well, but I see that we don't have so much time. I need maybe 5 minutes more. Wow. Okay, so the first question was what is conventional light water reactor nuclear fuel made from? Okay, no surprise. Almost all understand right. It's uranium, zirconium, plutonium. Well, but even when French colleagues use plutonium in the fuel, the cladding is still zirconium, not stainless steel. Stainless steel is in fast neutron reactors is used. What else? What stage of the nuclear fuel cycle sets the requirements to the characteristics of the fuel? Interesting result, by the way. In fact, all these stages influence on the characteristics of the fuel, but the right answer is the third one, irradiation in the reactor, because electricity is the central point of the nuclear fuel cycle, electricity production. So it means that we produce fuel just for electricity production. And that's why reactor for us is the central point, and reactor determine all the requirements for the fuel. It's also determine the characteristics of the spent nuclear fuel. What are the dangers inherent in spent nuclear fuel? Well, okay, radioactivity and heat generation. You're absolutely right. Okay, before we step into the outcomes and your questions to me, I'd like to show you just two simple slides. They are about radioactive waste, and they are very good. Okay, I could do it by myself. And they are again about sustainability and understanding of sustainability. Look, there is no industry that can operate without the waste. This is the law. So nuclear industry is not an exception, and we also produce the waste. And this waste is, when we're talking about light water reactor, could be split into the three main routes or three main categories. First is operational waste. The second is decommissioning waste. So when we dismantle when we dismantle the reactor after it's closed. And the third one is spent nuclear fuel, or used nuclear fuel, we sometimes call it so. It's more or less clear what is about operational decommissioning waste, but for used nuclear fuel, as we know, there are different ideas. We propose reprocessing, and in this case, the only waste that we send for the final disposal is the short-lived fraction of cesium and strontium. And in this case, when we use this technology, all the waste generated by the nuclear power plant could be arranged at the same place, at the same site, and could be disposed at surface or at depth disposal. And you can see here, this is the so-called universal radioactive waste disposal facility, which is designed especially for this case, for this recipe. And you can see here three different zones. The first one is for very low level waste. It's clear. Everybody understand it. The second one is for low level and short-lived intermediate waste. And the third is for long-lived intermediate waste and short-lived high-level waste. The most dangerous one is which one? Well, any ideas? This one, the short-lived fraction, which is cesium and strontium. And it has to be disposed at a depth of about 70, 72, maybe a little bit more, but well, the scale is the same, 72 meters. And in this case, the total area of the site, which is designed for the 2 units of VVR, 1 gigawatt power after 60 years of its lifespan, is just 22 hectares. 22 hectares is a rectangle with a size 400 meters by 550. So it is about 3 football fields. And you can imagine that 60 years of working of two big units, billions of terawatt hours of electricity, and just 22 hectares of waste, which is compactly and safely packed and isolated at the same site. This is sustainability as we know it, as we understand it. So, well, all the lifespan and just 22 hectares. Now, this is the conclusion. So now I'm finished, and I would like you to remember after my presentation just 7 simple ideas, simple things. First one is nuclear fuel cycle must be sustainable. In case we are not sustainable, nuclear industry will die, because the reality is that environmental agenda is very strong, and well, we have very many ecological activists, and altogether they will burn us. Then, the kernel of sustainability in the nuclear fuel cycle is its closure. So we have to close the nuclear fuel cycle, we have to recycle the fissile materials, and at the same time we have to reduce the amount and danger of the waste to be finally disposed. To perform sustainable nuclear fuel cycle, it's necessary to partition the spent nuclear fuel into different fractions and to find the certain way for certain fraction. The main challenges are here. Uranium-plutonium recycling is clear, so we have to understand how to do it, where to do it. Then minor actinides partitioning and transmutation. Then short-lived fraction conditioning and characterization. And finally, technology for its safe isolation. Rosatom knows how to meet this challenge. All necessary technologies are mastered already. Commercial solution is offered as well. And the name of this solution is sustainable nuclear fuel cycle. Easy to remember. The 6th one, the name of the solution. Sustainable nuclear fuel cycle. It includes everything that NPP operator or spent nuclear fuel owner needs for ensuring and to guarantee long-term operation of the fuel. Rosatom is open for cooperation and education. So follow us and let's make the life better. So finally, the common task for you. If you're interested in the topic, there are 3 recommendations of mine. The first one, if you like to know more about it, is everything concerning partitioning and transmutation. Sometimes it's the abbreviation of this technology or the sets of technologies, PNT. And please find anything you can find in the internet and read about it. As for me, the main or the best explanation or the best description of this technology was made by German scientists. I don't know why, but Germans are very comprehensive and very, how to say, strong in understanding of the main problems, in understanding of the general situation, and they explain everything very good. So find it. Another one, I know that this morning it was a lecture by Dr. Shadrin, and he represents as well. He represents the project PRORIF. It's very interesting, very exciting. So any articles, any news about PRORIF, the keywords you can see: breast, it's the name of reactor, dense fuel, pyrochemistry. I guess that he pointed your attention that at the same site, at the same time, they create there the whole nuclear industry just on the small side. So reactor, fuel fabrication, fuel recycling, everything is made on one side. And well, it's fantastic, really fantastic. Very many interesting technologies, interesting solution. And by the way, sometimes people say that PRORIF technology is competitive to the sustainable nuclear fuel cycle. It's not true, because sustainable nuclear fuel cycle was designed for light water reactors, for the conventional reactors, which you can find all around the world. But PRORIF doesn't need any light water reactor. They work just with the fast Newton reactor, with the breast, and they don't need anything from outside, just maybe depleted uranium, and that's all. So any articles, any interview, you're welcome. And don't forget about sustainable nuclear fuel cycle. We also publish interview, articles, news. Sometimes we are called as balanced nuclear fuel cycle. Don't be embarrassed. It is also our name, but well, you can find it also in the internet. And that's all. Thank you very much. Here is my contact. You're always welcome. And if you have any questions now, I'm ready to answer now. If not, just remember my contacts and send your questions to me.
Thank you very much. Dear colleagues, any questions?
Thank you, Mikhail, for this great presentation. It's not only with a lot of information, but also in a very funny way. I like it very much. I would like to ask about this commercial project to take the spent nuclear fuel from the foreign countries and transport it to Russian Federation, reprocess it, and send the short-lived fraction back to the foreign country. From the Russian law, we cannot accept the foreign spent nuclear fuel.
No, we can.
We can. Okay. Because as I heard that we can accept only fuel that
Russian
we
it's not true.
traded.
So is it the
before.
question? I'm ready.
Yeah,
to
yeah,
answer.
it's a question.
So Russian legislation is not easy, let's call it so. It's more or less understandable when you treat with it for maybe for a month, but from the first side, sometimes you can make a mistake. So we have the possibility to get spent nuclear fuel from abroad, either Russian origin or fabrication or foreign origin. But in case we get Russian fuel, it's much easier. The procedure is easier. So it is just intergovernmental agreement and commercial contract. That's all. If the fuel is fabricated abroad, Westinghouse, for example, or Framatome, we also can get it, but in this case, we have to get additional approval by the special commission, which consists of the representative of the different federal bodies, authorized bodies. And in fact, there was no a case of the solution of this commission. Well, maybe it's our, how to say, bad work, because I represent Tenex, who is responsible for foreign trade contracts concerning the spent nuclear fuel, and all our customers, as for now, used Russian origin fuel. But we also discussed this issue with other countries, and well, you can believe me that when we understand each other and when we understand the condition, not the government solution, but the commercial condition, I think we will go to this commission and get the approval.
So after the first case, everything will be easier. Yeah.
Yeah, sure. First time is always difficult, but
Yeah, that's true.
Second is much easier.
Any more questions? Yeah.
Thank you for the very nice and interesting presentation. My question is that it was mentioned that fuel before irradiation and spent nuclear fuel are vastly different in their characteristics. And I understand that no chemical process, no separation is perfect. There are always some leftover materials that you want to separate. So when you reprocess the fuel and get back to useful materials and you make fresh fuel out of it again, does that still possess the same safety that the original fuel possesses right after mining, so you can still handle it safely, or does it have some contaminants that make its handling a bit more difficult, for example, for MOX fuel or just reprocessed fuel?
I see. It's not contamination. It is the characteristics, the internal characteristics of the fissile materials. Because when we get the uranium and plutonium from light water reactors, there are very many, there is no uranium 38 and 35. There are very many other isotopes, and some of them, like 32 and 36, create additional gamma field radiation. So it means that even if you use fuel, fresh fuel, made of just reprocessed uranium, nothing else, the gamma dosage from this fuel will be higher than the natural uranium-based fuel, and the operator of nuclear power plant has to make some additional measure to protect its personnel from this additional dosage, and that's all. When this fuel goes to a reactor and irradiation started, there is no difference. It's the behavior is the same. When we are talking about MOX fuel, the case is much more serious because plutonium gets well even more how to say radiation from its side, and once again the operator has to make more protecting measures, more protecting activities, and well, finally, the fuel behavior is also different, plutonium-based, and well, but neutron physics knows what to do. So it's not about the contamination. The surface is clean in any case, but the characteristics of the material inside is different. You're right, but we know how to deal with it. I mean, industry knows what to do.
I have another small question about the short-lived fraction. If the foreign country doesn't have a repository storage for this fraction at the moment, is it possible for Russia to store it for some time before the foreign country will create its storage?
Yeah, absolutely right approach. So we are, how to say, we are the friends, not just the partners, but also the friends to our clients, to our customers. And for sure, we make the roadmap of all the used nuclear fuel and high-level waste activities altogether, with understanding of their possibilities, our capabilities, and well, all the restrictions, all the requirements that they have. Surely, we could keep the short-lived fraction for some time at the Russian side, and we also, by the way, this one, which was with these beautiful pictures. Sometimes we call this solution as the fifth element of the sustainable nuclear fuel cycle. So you have seen the 4 components, it could be fifth. In fact, by the law, the responsibility for the waste disposal belongs to the country of origin, because it becomes to the country where a nuclear power plant is operating. That's why, well, we could not include it as it is into the sustainable nuclear fuel cycle, but we can help to our customers with this object, with this facility, and we can how to say приземлить. Yeah, so we could arrange this design because it's typical design, it's universal design. We could make it, we can make localization of this design to the site of the customer. And it includes all the solution concerning the short-lived fraction. So if they need some more time for construction, if they need some more time for cooling of this fraction, it could be realized also in Russia.
Thank you. Any more questions? If not, let's thank the speaker again.
So once again, I clearly understand that the topic is not so easy sometimes, especially in my, how to say, presentation. That's why, once again, my address, email, you're always welcome. Thank you. Нужно? Зовите.
So let's continue. And now just, I would say, not very long information about the storages for spent nuclear fuel. And in the beginning, just again, very short historical overview, because we talked a lot about the reprocessing of spent nuclear fuel, and we discussed that the main idea, the main goal of the reprocessing of nuclear fuel or irradiated fuel was the extraction of plutonium for the nuclear weapons production, etc. But the problem for storage of spent nuclear fuel or irradiated nuclear fuel was the first key aspect in the treatment of spent nuclear fuel. Also, even when the industrial or commercial application of the nuclear energy started, in the beginning it was just a few nuclear reactors with not very large energy production, maybe 100, 150, 200 megawatts of electrical energy. So there were no need actually in reprocessing in the very beginning. So the main treatment of spent nuclear fuel was the storage of the irradiated or used or spent nuclear fuel. So many synonyms you already know. And during the storage, it was it was searching for the next, for the future solution, what to do with this spent nuclear fuel. But in at the end of 60s, beginning of 70s, or in the 70s, it was a rapid growth in the number of nuclear power plants. So thus it was a need to increase the storage facility, to make the new techniques for the storage. And since the amount of spent nuclear fuel increased every year, at that time, the main idea became a reprocessing of spent nuclear fuel to extract valuable components, fissile components, and use them again. But the history is very strange in this topic. As you remember, at the end of 70s, it was a ban in the USA for the reprocessing of spent nuclear fuel. So these ideas for the creating of new reprocessing plants was slowing down. Also, it was a Chernobyl accident. And due to the accident at Three Mile Island, so due to these events, let's say the idea for reprocessing of the spent nuclear fuel will become not so popular. And even even the facilities that were initially designed for the reprocessing of spent nuclear fuel at that moment become just as storages for the spent nuclear fuel. One of the example, probably you've heard about the site in Germany that is called Gorleben. That was supposed, me personally, I know this place because it was supposed to be a final repository for the spent nuclear fuel, but I didn't know that before that Gorleben was designed to be a site for the reprocessing of the spent nuclear fuel. So it was underground. The idea was to create underground reprocessing plant for the spent nuclear fuel that would locate in the former salt mines. So it seems that it would be very good from the safety point of view. So you have no water intrusion. It is underground. So in case of any accidents, the environment will be safe.
But again, due to these negative events in the history of the nuclear energy, these ideas, they were stopped, and this site, Gorleben in Germany, was used only for the storage of spent nuclear fuel, not for the reprocessing. And now there is a moratorium for the use of this site at all. But now, since let's say beginning of this century, 20 years ago maybe, the rapid growth, the great interest was increased, especially in Asian countries, in East countries, in India, in China, in other countries, and there is again rapid growth of the number of the nuclear power plants, and again the number of the spent nuclear fuel is increasing, and again the main idea become the reprocessing of spent nuclear fuel. But there is still a huge need in the storages of spent nuclear fuel, and it is not only the final repositories as for the open nuclear fuel cycle, of spent nuclear fuel, but the interim storages, so for just storage of spent nuclear fuel before its reprocessing. And today, since the 1954, when the first nuclear power plant started operation, it is more than 400,000 tons were unloaded from the all the nuclear power plants, industrial nuclear reactors. And at the moment, only 1/3 of this amount is reprocessed. So the rest, around 260,000 tons of spent nuclear fuel, is still in interim storages and still stored and looking for the further solutions. If we will look what is the situation now, where all these spent nuclear fuels are stored, you can see that more than the most part of the spent nuclear fuel is stored at nuclear power plants in the cooling pools that are located at nuclear power plants. So it is wet storages, so around 60% of all spent nuclear fuel is in this type of storages. Around 22% in also at NPPs, but in dry storages, and only a small fraction, around 15%, is in centralized storages of spent nuclear fuel. So there is specific requirements for any type of spent nuclear fuel storages. Of course, first of all, it is a safety for the spent nuclear fuel, and as far as spent nuclear fuel still contains a lot of fissile materials, that means that it is very important to provide subcriticality. So that means that there would be no chain reactions with this chain nuclear reactions. As far as you already know, and you answered these questions about the difference between the fresh and the spent nuclear fuel, there is a huge heat release from the spent nuclear fuel. Thus, there is a need to remove this efficiently, this heat. And it should be so efficient that the temperature would not exceed the established limit to exclude degradation of the cladding, of spent nuclear fuel cladding, of the materials, of the biological shielding, of the materials of the containers, of the facility itself. There should be a biological protection to avoid any additional doses for the personnel, for the people who are working there, and for the materials that are used there. It is ensure the that there would be no release or minimum release of the radionuclides in the environment. And it is important to be able to monitor the conditions of the spent nuclear fuel during the conditions of storage of the spent nuclear fuel, the parameters of spent nuclear fuel, and to control the operations during the handling of the with the spent nuclear fuel. And there is specific safety guide at IAEA about the storages of spent nuclear fuel, where you can find information about these requirements and some cases for the storages. So, as I mentioned before, there are two main types of the storages, wet storages and dry storages. And wet storages, it's normally just huge pools, huge constructions made of cement and covered with the, so inner space is covered with the stainless steel with the thickness of 3 to 5 millimeter. So normally walls of these pools, they're covered with the 3 millimeter steel and the bottom is covered with the 5 millimeter steel. So it's a huge pools with the depth of 10 to 15 meters and the other parameter sizes can be very different depending on the design of this pool. So the advantages of the wet storages that we are using water, so there is a high heat removal from the spent fuel from the spent fuel assemblies. There is a possibility to use a boron absorber, just boric acid, for example, to avoid this supercriticality of the fissile materials. As far as water is very clean there, it is possible to make a visual control of the conditions of storage and the parameters of the spent nuclear fuel itself. And water itself provides a very good biological protection. So it is a joke, but like based on real parameters that you can swim on the top of this water, even if the spent nuclear fuel is inside the pool, inside the pool. And there are some certain requirements for wet storages. So of course, all of them taken into account these general requirements, but there are some specific requirements. So that includes the maintaining the subcriticality at any probable water density. That means that even if there is loss of cooling system, if the water starts boiling, still the conditions for the storage of spent nuclear fuel should provide the subcriticality. It is made with the use of different materials of the racks where the spent nuclear fuel is stored. So another requirement, so if we are using this neutron absorber, like boric acid, for example, the design of the facility should provide the enough safety that even if for some reasons, due to technical operation, due to technical mistake, if the water with absorber will be replaced with just distilled water, there will be no emergency situation even in this case. Again, for the good heat removal, there is certain requirements for the temperatures of the water. It is use of the special techniques to reduce or exclude the release of radionuclides into the environment. There are specific filtration ventilation systems, control for the water quality to avoid any degradation. There is from the design of the pool, there is no possibility of the pool water leakage. Not always, or as it was mentioned in which lecture? No, I forgot about the Fukushima accident. Yeah, these storages of spent nuclear fuel, they are located not in the bottom. They are located on the top, near the top of the reactor building. So there could be leakages due to the holes in the bottom, and then due to the damage of the pool, and if the water is released from the pool, it can be overheating of the spent fuel assembly, so it's not very good. Again, it is as far as water should be clean, it will provide necessary transparency during the reloading operations, during the handling of the spent nuclear fuel assemblies, and there should be indicators for the water level. If it becomes lower than necessary, then it will indicate that something went wrong. So on this wet storages, they have different designs, and we will start to see different, not designs, but cases of the wet storages at nuclear power plants. So it is either near reactor pools of the spent nuclear fuel, or just spent fuel pools at nuclear power plants. These pools, they can locate outside of the containment of the reactor buildings. So the main part inside the containment, of course, is the reactor. Yeah, and this pool for the storage of spent nuclear fuel can be located outside of this containment, and fuel assemblies, they are transported through the transporting corridor. It is the same for some design of the PVR and BVR reactors, so pressurized and boiling water reactors. Here you can see that this spent fuel storage pool is located outside of this primary containment. Sometimes these spent fuel pools can be located inside the containment, like in the case of the nuclear power plants with the reactors VVR 1200. You can see here is the reactor vessel itself, and the spent fuel pool just near the reactor. In the case of the EPR reactors, design the reactor is here, and the spent fuel pools is located just not very close to the reactor, but still inside the outer containment of the reactor or nuclear power plant building. In the case of the RBMK reactors, again, the spent fuel pools, they are located close to the reactor, also in the building, in the same building. And they are connected with the transport corridor. And in the in the earlier stages, and the first first designs of the nuclear power plant with RBMK reactor, these panels with the spent fuel, they were also filled with water. So the spent fuel assembly were placed in the special panel that is hanged in the pool, and inside the panel there is also water, distilled water. But nowadays, as I understand, there is no use of the panel, so there is a hanging of the spent fuel assemblies without panels. It's a generic designed for the spent fuel pools at PVR's reactor. Again, there is a reactor vessel itself. There is a transporting corridor. There is a transport of the spent fuel assemblies to the pool, special pool, and there are different control systems that are controlling the quality and the level of the water. There is specific systems to detect the leakages through this pool. And of course, there is a system for the conditioning the water to prepare the distilled water or to mix it with this boric acid to prepare the composition of the aqueous solution that is used in this type of the spent fuel pools. The spent fuel assemblies, they are stored not just laying in the pool or hanging like at RBMK types of the reactor. There are specific racks that are designed for different types of the fuel. And in the first cases, these racks with the open frames with the low density of the fillings of this rack were used because, again, it was not such a lot of spent nuclear fuel, so there were no need for the dense arrangement of the spent fuel assemblies. That's why these simple racks were used. The water, so they are open walls, so the water just flow through these walls to cool down the spent fuel assemblies. But with increasing the amount of the spent nuclear fuel, it becomes necessary to increase the density of the location of the spent fuel assemblies in the pools. And but there is a problem with the criticality. So there is a need to provide special shielding of the spent fuel assemblies from each other. So the next designs, they were not the empty walls. Yeah, it was like walls, let's say, that were made of stainless steel. Again, stainless steel can work in distilled water very efficiently, so with no corrosion for the very long time. It was estimated that the corrosion of these materials is around 1 micron per year, so it's very low rate of the corrosion. And with different designs, with different density of this arrangement of the spent fuel assemblies, different racks were designed. In this case, water was passed not in horizontal direction like here. Yeah, there is empty walls, so the water can just pass through these walls. But water was transported from bottom to the upper outlet of these racks, so the water flow is not horizontal but vertical, let's say, in these racks. And also for very higher density of the arrangement, specific materials are used. It is stainless steel with the addition of the boron carbide. Boron is a neutron absorber. It is either stainless steel or aluminum with the addition of this boron carbide to provide the subcriticality in these conditions. The same is for BVR reactors. Again, first racks that were designed were with low density, with this huge distance between the spent fuel assemblies. So if you have just few of the fuel assemblies, you can arrange them, you can place them far away from each other, and then there is no problems with the criticality. Yeah, but if you have a lot of spent fuel assemblies and you place them close to each other, then there can be a problem, and that's why it is important to use these neutron absorbers as a component of the stainless steel or aluminum that are used for construction of these racks. Here you can see it is a stainless steel rack with the addition of the boron. For VVR reactors, again, it is dependent on the amount of the spent fuel assemblies in the pool. It is possible either to use the low density rack or high density rack. They are made of aluminum, and again, with the addition of the boron compounds. And what is interesting for this structure of the VVR pools for spent nuclear fuel, that there is additional camera number three here that is designed for the not here. There is a specific here for the fuel assemblies with the defects. So that means that in this pool it is possible to place the spent fuel assemblies with the defects. Of course, they are placed not just in the water. They are first placed in panel, in additional container, let's say, as RBMK fuel assemblies. And in these special panels, they are stored inside the spent fuel pools together with all other spent fuel assemblies. So it is advantage of this type of the design of the spent fuel. This view, just a photo from the inside of the centralized wet storage that is located in Krasnoyarsk region in Mining Chemical Combine. It was started in 1985, and it was designed for VVR 1000 spent nuclear fuel. And you can see that actually, there is no open water. Yeah, so all the water, the whole area of the pool is covered with the lid, let's say, and people can walk there without any problems. Again, I remind you that water itself is a good has a good biological protection ability. So there is no additional doses at the level of the top water level. Yeah. So these lids, they are open when there is a need for changes for transportation of the spent fuel assemblies, and yeah, all the operations are visible because water is transparent. There is again, depending on the amount of the spent nuclear fuel, there is different possibilities to arrange this fuel assemblies, either in a uniform way, where you have all the racks with the equivalent heat production and radiation production, or depending again on the amount of the spent fuel, you can arrange it in these orders. Either each of the hot assemblies is surrounded by 4 cold or empty assemblies, or each of the hot assemblies are surrounded by 8 cold or empty assemblies. So going back to our 2 types of the storages of spent nuclear fuel, it is either wet storage, or dry storage. And dry storages, they can be different. It is either the container type of storage, or the specific facility for the storage. But just a few words about this spent nuclear fuel storage facility in Sweden. It is interesting because in this case, it is, as in the case of Gorleben, but it is dry storage. Here, it is also underground storage facility with the depth of 32 meters. These cooling pools, the spent fuel pools, they're located underground. So it's again very safe, and it is probably only one wet storage facility underground, and it is located in Sweden. But now about just few words about the dry storages. So why in wet storages, it seems like everything is fine. All your spent fuel assemblies that are very hot, actually, they are located under the water. They cooled very efficiently. The water itself has a good protection properties. Why we need dry storages? But dry storages has much more advantages. First of all, because they're much more easy to operate. You don't need to have a special system for preparing the water. So again, I remind you that in wet storages, distilled water is used. Here you don't need any water at all. You just need a good designed containers. So it is much simpler to construct dry storages, to maintain them. It is much less in time and cost, the construction and operating the dry storages. There is no secondary or lower amount of secondary radioactive waste, again, because there is no flow of the water that you need to clean after the pool. If there will be a need in decommissioning in future after, let's say, 70, 100 years, it will be much simpler, because everything is located on the ground, and no wet, no liquid radioactive waste there. And you can extend the size of the dry storages very easily again. As for wet storages, as for any kind of storages, there are some specific requirements for the dry storages. As usual, it is ensuring the subcriticality of the spent fuel during any kind of operation, either loading or transporting or reloading, unloading, and storage itself. It is exclusion of the penetration of water, because water is a good moderator for the neutrons, so there should be no water. That's why it's dry storage. The heat removal parameters should be designed depending on the climate conditions of this dry storage, and to make it possible to maximize the passive heat removal from the spent fuel assemblies. There is requirements for the inert gas filling or filling of the dry storages, because if you fill the internal space with the inert gas, it makes it more safe, the storage of spent nuclear fuel, no corrosion, or let's say even lower rates of corrosion if we use inert gas inside the storage cask of the spent fuel. So just several examples of the dry storages. First, storage in containers. For this type of the storage in containers, the design of containers is made to provide the cooling of the spent fuel assemblies and the internal space of the container just by the natural convection of the air. So there is no need in pumps or any other mechanisms to make this flow of the air. We know that the warm air goes up, so the design of the container is made so that there is a natural flow of the air. There is a general view of the metal container for the VVR 1000 spent fuel assembly. So you can see these hexagonal channels for the internal basket, because as you know, Russian design of the spent fuel assemblies, it is a hexagonal shape. There is channels for the neutron absorbers. It is either boron doped steel or aluminum rods. It is a special called planes, but special parts that are used for container catching and transport operations to handle the container shells, the fixed shells, of course, and the lid with two lids that contains the monitoring outlets. It's not very good visible. Monitoring outlets and other outlets. And yeah, there are safety requirements, as it was in the lecture about the transportation of the spent nuclear fuel, that there are a lot of different requirements and a lot of different tests that are made for the containers for transporting of the spent nuclear fuel, like the stability during the falling down. Here it is from 9 meter height. It is also the resistance to fire, and other very tough tests. And all these containers, they are also designed to withstand the accidents with the airplanes. So if even the Boeing 747 will go to the containers, they will withstand this accident. There is another dry type of dry storage facility, so it's not a separate containers, but it just cementitious containers with all these metallic parts inside. And for Russian Federation, there is quite new, so it started in 2012 operation, quite new centralized dry storage facility, also at the same place, mining chemical combine in Krasnoyarsk region in the city of Zheleznogorsk. So it is not containers, it is a facility with the cells for the fuel assemblies. And there is also a natural convection of the air, so there is no additional pumps for cooling down the fuel assemblies. It is natural convection of the air, and yeah, it is designed for RBMK spent nuclear fuel. And I would say that for this facility, mining chemical combine, there is not only wet storage, where is here's wet storage that I showed you in the photo. There is a dry storage. There is also a platform for the containers to see. So to make a reference for the container storage. And here, as Andrei Shadrin also mentioned, the new pilot demonstrating center for the reprocessing of spent nuclear fuel is located. And there are plans for future to create a new big plant, not a pilot plant, but industrial reprocessing of the spent nuclear fuel with big capacity, but it's just the plants. Nobody knows will it be there or not. So I think that is all for the storages of spent nuclear fuel. If you have any questions in this part, no. Okay, thank you. Now I think we can have a short break. Нет вопросов. And I would say that we would start at 4:30. Yeah, so in 15 minutes, not to wait a very long time. Okay. So let's start the final lecture for today, not for the school, but for today. And first of all, at the beginning, I would like to thank Professors Sergei Kulyukhin and Michael Odjovan for their materials. I take some of their slides in this presentation. So, and we will talk about the systems for the off-gas treatment, and just a reminder that the radioactive waste that are produced during any operations of with the radioactive materials, they can be in different aggregate states. They can be in gaseous form, in liquid, and the solid form. And about the liquid and solid form, it was a lecture before, and today, and now we'll talk about some gaseous. Thank you. Gaseous radioactive waste, and the problem with the gaseous waste that they're very mobile. The most mobile type of radioactive waste, and they can be stored, but as far as they're very mobile, the main procedure should be the treatment with the purpose to convert them in the liquid or better to the solid form, and these forms can be further processed for the safe storage and further disposal. And there is several books from the IAEA safety standards for the about the discharges of the radionuclides in the environment, where you can find the information about the discharges for gaseous, liquid radionuclides, but also maybe one of the main documents. It is a technical doc number 1744 about the treatment of radioactive gaseous waste, and Dara and Michael Odjovan is one of the contributor to the treatment of radioactive gaseous waste to this technical doc, not only to this one, but to this specifically. And there are other technical docs at the IAEA website, where you can find information about the treatment of the gaseous waste from different facilities, from of different composition, with iodine, with carbon, with tritium, and other. And so these technical docs, they're different because, as it is written here, all the gaseous waste, they're unique. Yeah, they are not the same, and that's why the systems for the treatment of these gaseous streams of the radioactive substances, they must be designed for each facility with the information about what types of the radionuclides are released there, what types of operations are there, what the temperature of these operations, what the humidity, etc., etc. So gaseous waste, as I mentioned before, they are produced almost every time when we are working with radioactive materials. And the problem that it is not only volatile compounds like noble gases, for example, like radon or different isotopes of xenon or krypton. It is also the formation of aerosols that are considered also as a gaseous waste. And you can see that at any type of facility, when we are working with the radioactive substances, even in medical centers, in scientific institutions, we produce the gaseous waste. So during the normal operation of different types of the reactors at either at nuclear power plants or research reactors or transport reactors, floating nuclear power plants. During the normal operation, there are 4 main groups of nuclides that can be released in gas aerosol emissions. It is, of course, inert radioactive gases or noble gases, argon, xenon, and krypton, the radionuclides. It is different types of radioactive aerosols. It is volatile compounds of tritium and carbon-14. Either it is water or it can be just hydrogen. For carbon, it can be CO2 or just a monoxide of carbon CO. And that is very important, different volatile compounds of the radioactive iodine. For the facilities where nuclear fuel fabricated or where the isotope separation is processed, there can be formation, of course, of gaseous hexafluoride of uranium. It can be formation of the hydrolysis products of the uranium hexafluoride, mainly uranyl fluoride, and fine aerosols of the nuclear fuel. And at MOX fuel fabrication plants, there can be the same aerosols but containing plutonium. So they're even more dangerous, even more hazardous. The MOX fabrication plant, from this point of view, can be very hazardous. During the reprocessing of spent nuclear fuel, there are a wide variety of the gaseous radioactive waste can be produced depending on the reprocessing scheme, depending on the composition of spent nuclear fuel that is dependent on the initial composition of nuclear fuel and the degree of the burn up of this fuel. Various volatile components can be produced. For typical operations during the spent nuclear fuel reprocessing, the first stages, tomorrow we will talk about these operations more, but the first stage is the cutting or chopping of the fuel assemblies and fuel rods. So during this operation, different radioactive aerosols can be formed containing components of the nuclear fuel, so it's fine aerosols, including components of the cladding, for example. Of course, as far as inside the fuel assembly and fuel rods, there are inert gases, noble gases, they will be released as well. And during the further dissolution of the spent nuclear fuel in the nitric acid, another gaseous products like carbon, for example, carbon-14 can be released because carbon-14 is not soluble in nitric acid. So CO2 will be released from these solutions. And some other components like just water droplets and aerosols with the solution of the spent nuclear fuel can go to the gaseous phase. There is another type of the head operation that is called voluxidation or volume oxidation. It is a treatment of the spent nuclear fuel with air, with oxygen, or with other gases for several reasons, for several purposes. First of all, it is to make it easier for dissolution of the spent nuclear fuel, especially, so maybe not only uranium dioxide, but with the plutonium, there are some problems for the dissolution. But also another purpose is to remove volatile fission products. With the heating of the spent nuclear fuel, first of all, inert gases will be released, then tritium can be released easy, so you can not have tritium in the aqueous solution during the further reprocessing. Carbon-14 will be released, cesium, technetium, molybdenum isotopes, and ruthenium isotopes also can be removed from the spent nuclear fuel, and so there will be less problems with the reprocessing of the spent nuclear fuel to handle these aqueous and organic solutions. Pyrochemistry that we discussed last week. There is always a system for the purification of the inert atmosphere inside this camera for the pyrochemical process. And so pyrochemistry is one of the options for the non-aqueous processing of the spent nuclear fuel. And as we discussed also, it can be fluorination of spent nuclear fuel for further separation of the uranium hexafluoride and other fluorides of the components of the spent nuclear fuel. And this fluorination is made with the fluorine gas or hydrofluorine. And for these types of the reprocessing, pyrochemical and fluorination, as far as in pyrochemistry, we're using the molten salts or liquid salts. They also can form these aerosols, so to form in this case, it will be not a water vapor, but particles of the chlorides of lithium and potassium, including actinides and the fission products, and they will go to the gas phase. Also, if you remember, I showed that there is a constant flow of the chlorine gas, so bubbling through the molten salt that also produce some kind of aerosols, and all these aerosols goes to the gaseous phase. Here again, as in the case for the fabrication and enrichment facilities, there is a possible formation of the fluorides that goes to the gaseous phase, and also if there are some technical problems, and water will penetrate into the system, it can be also a hydrolysis product of the uranium hexafluoride and other fluorides, the hydrolysis products. There are some special treatments of the solid and liquid radioactive waste with the use of high temperature processes. One of them it is use of the plasma incineration. It is device called Pluton at the Radon facility near the Moscow. So there is a plasma that burn out all the solid or liquid waste to the ash. It is not even the ash, it is like a glassy ceramic material at the end of this furnace. And of course, as there is a burning of all the materials, there is a strong intensive flow of gases containing the radionuclides, and you can see there is a number of equipments to catch this radionuclides, that the air that goes out will be clean, and the concentration of the radionuclides in this outlet will be below the exemption limits. There are also safety standards for the radioactive waste storages, of course, where it is written the requirements for the purification of the gas emissions in this ventilation system for the radioactive waste storages. And also, even when we are starting with the natural compounds with natural radioactive materials, there is a risk to produce radioactive aerosols containing the natural radionuclides. There are also non-radioactive gas emissions due to the chemical operations. It is starting from dust or fly ash. It can be hydrochlorine. It can be formation of sulfur dioxide, different oxides of nitrogen, especially during the operation of the spent nuclear fuel dissolution. There can be a formation of carbon monoxide and many other compounds due to the thermal decomposition of radioactive waste, for example, etc. And there are, just few words about the aerosols. I mentioned that a different process, either when we are working with the aqueous solution or when we are working with the molten salts, there can be a possibility of the formation of different aerosols. And aerosols, actually, it is a suspension of the solid or liquid droplets or small particles in air or in other gas if we are working in inert atmosphere. And these particles, of course, with the flow of the gaseous phase will go together with gases, and as far as they can contain radionuclides in solid or liquid phase, they will be radioactive, and we should handle them, treat them in efficient way to remove all the radionuclides from the gaseous phase. And depending on the if it is solid or liquid droplets, depending on the size, how they are generated, there are different terms for these aerosols. There is a typical diagram for these different kinds of aerosols, depending on the size of the droplets, and the equipments that can be used for removal of these droplets, of these aerosols from the air. The typical equipment for removal of the aerosols, it is wet filters, it is high performance filters, and it is electrostatic separators or precipitators. They're working for the very small particles, less than 1 micron, and depending on the design of the filtering system, there can be different productivity. But you can see that these types of the filter systems, they can be very efficient in the removal of the aerosols and removal of the small particles from the gas flow. And let's look on some other equipment. One of them is called Venturi scrubber. It is one of the typical equipment that are used not only in radiochemical plants, but in different applications for oil industry, for chemical industry, to remove small particles like ash, for example, from the air. So the principle of the Venturi scrubber based on the Bernoulli principle, we remember from this general physics, hydrodynamics, that in the smaller the section of the surface of this section, the lower will be the pressure in this part of the vessel. So if we put our airflow in such a device where here the surface of this section is smaller when in the beginning, here the pressure will be lower, but according to the Bernoulli's principle, if we have lower pressure, that means that velocity will be higher. That means that when system goes through this neck, through this not neck throat, there is increasing of the velocity of the gas flow, and in this section there is the velocity is so high that there is not a laminar flow but turbulent flow, and with this turbulence there is a possibility if we add additionally some water droplets, yeah. Here is an addition of water. There's inlet of just water due to the turbulent flow. Droplets they are disintegrated. They are forming very small particles, not particles, but small droplets. And these small droplets, as far as they have high surface area, relative surface area, they absorb on the surface these solid particles, this dust or fly ash, and then when this flow goes to the next part of the Venturi scrubber, there is a wider section. That means that the velocity become again smaller, and under these conditions there is a recombination of droplets to the bigger drops, and then the formation of the normal stream of the water that contains all these ashes that were absorbed on the surface of small droplets. So these Venturi scrubbers, they have different designs depending on where this water is introduced. It can be introduced from the upper part. It can be introduced directly in this throat section of the scrubber. It can be introduced from the horizontal stages. It can be not only one stream, but it can be like several streams of water inlets. So different designs of the Venturi scrubbers. They are very simple, but so they are used to remove solid particles from not only solid but aerosols from the gaseous streams. Another type of not the same technique, but also based on the airflow inside the equipment. They're called cyclones or cyclone precipitator, if I remember correctly. So there is another system. There is an inlet of the air, and here the direction of this airflow is designed so to form the vortex inside the equipment. So when this aerosols goes through the vortex, all the particles they are going to the walls of the equipment, and then concentrated or precipitated at the bottom of the vessel, and they're collected there. So all the particles they are again aggregated on the walls of the cyclone equipment, and the air just going up and goes the pure, not pure, but without aerosols at least, goes out. Cyclones, depending on the types of the aerosols, they can be less efficient, but in this case, there is no need in water inlet, so it can be more preferable in terms of the formation of secondary waste, yeah, because here this flow of the water, it is a secondary radioactive waste that must be treated further. HEPA filters, I think many of you are quite familiar with the HEPA filters because they're used everywhere in normal techniques at your home when you make a cleaning in the room. Or when you are using air conditioners, so they're used everywhere. So the HEPA filters are very efficient for removal of very small particles, like 200 nanometers size can be efficient even for such a small particles. But HEPA filters, they're sensitive to the conditions of the gas flow. So before the use of HEPA filters, there should be, of course, some other pre-filtering systems. Some of them very simple, like use of I don't know, gravel, for example, or other big filtering systems to remove all the big particles. There can be use of zeolites to remove the humidity, and then for very fine particles, the HEPA filters can be used. So they normally are the last filters of the purification system. Electrostatic precipitators, they also can be very efficient. There is charges on the electrodes, made of wires, and the aerosols that can be charged, they can be separated on different electrodes, and thus can be separated again from the airflow. And instead of HEPA filters, not like HEPA filters, they can be used even in humid conditions. So for chemical separation, there is a list of different techniques that can be used. It is either sorption on different sorbents. So you can see here the features and practical cases of application of different types of the separation techniques with the list of the limitation and the secondary waste formation. But let's go just shortly through these techniques. So as a sorption, for sorption, we can use different absorbers. It can be different filters as well, starting with the just normal filters like fabric filters, dry fiber filters using HEPA and other materials, even metallic and glass fibers. It can be wetted fiber filters. It can be paper filters that normally used in chemical lab. It can be, as I mentioned before, the granular filters with the fillings of sand, gravel, and other sorbents. It is already mentioned electrostatic precipitators. It is membrane filters and different metallic filters. For wet scrubbing or wet absorbing, it can be used Venturi scrubbers, multi-Venturi scrubbers, submerged gravel scrubbers, so again with the use of some specific liquids, or a submerged mesh scrubber. It can be special filters for catching the foams that are important when there is a possibility to for the presence of the surface active materials, and the cyclones that are already mentioned. For deposition of the non-radioactive macrocomponents like different oxides of nitrogen, of sulfur, of the maybe fly ash, there can be a formation or artificial formation of the aerosols. And to do this, it can be used just water, like with these different sprinkler systems. It can be different polyvinyl compositions. It can be ethylene glycol. They are used also, for example, for the treatment of the gauges during the vitrification of the high-level radioactive waste. Ethylene glycol, polyethylene glycol is used for to form like a film, not on the top, let's say on the top of the glass, to catch the gauges products, to decrease the rate of the release of the radionuclides in the gauges phase. It can be use of different volatile oxides and the hydrolysis of different compounds of tantalum or even zirconium or some other component like titanium or others. So some specific application for different radionuclides. First of all, tritium. Tritium can be present in the form of the water or as a hydrogen, like elemental hydrogen. For treatment of the gaseous flow with the tritiated water, one of the most efficient process is the use of the isotopic exchange with the vapor of just natural water. Due to the isotopic exchange, the concentration of the tritium in the gaseous phase is decreasing, and depending on the height of the column, so we can calculate the number of the theoretical plates there, depending on the design of the column. The separation factor or decontamination factor can be very high. Further concentration and treatment of the tritiated water can be done with the use of cementing. So the one of the main component of the cement is water. So the tritiated water will be just a component of the cement. But of course, these cementitious materials should be placed in hermetic vessel, because again, due to the isotopic exchange, the tritiated water from the cement can go to the air, and thus it is important to seal hermetically these materials with the tritium. Gaseous hydrogen with tritium, yeah, so it's like a molecular hydrogen, can be oxidized catalytically in the presence of some platinum catalyst or other catalyst to the tritium water, and then this tritiated water can be either purified with the use of isotopic exchange, or can be directly immobilized in the cementitious matrix. So carbon-14, also one of the important radionuclide, especially when we are talking about the nitride fuel, because nitrogen inside the nuclear fuel can be activated and form carbon-14. So another origin or another source of carbon-14 is graphite reactors. So it is very important radionuclide in the reprocessing of spent nuclear fuel or reprocessing other materials that were used in different nuclear power plants. So carbon dioxide can be absorbed from just the normal chemistry of carbon dioxide using alkaline solutions, or it can be absorbed on different sorbents, which surface will modified with different, let's say, functional groups that have also basic properties, like nitrogen containing groups, like amine groups, for example. These groups can also efficiently catch carbon dioxide. For example, to make the small impression how different amines be efficient for the carbon dioxide capture, for the analytical purposes, to measure carbon dioxide, it is possible to use the special liquid scintillator cocktail that is based on amines. So there is amines inside the liquid scintillation cocktail, so the carbon dioxide directly interacts with the amines, so it's carbon dioxide captured immediately in the liquid scintillation cocktail, and this cocktail can be measured. So this approach to use amines to capture carbon dioxide is well known and can be applied not only in liquid phase but also in the solid phase to capture the carbon dioxide. Carbon monoxide as a product of the not efficient oxidizing of the organic components can be captured by the pre-oxidation from monoxide to dioxide, and then just as mentioned above, this carbon dioxide can be captured in with different techniques, either using aqueous solution of alkalines or can be absorbed on different solid sorbents. Noble gases that are present in irradiated nuclear fuel, they're how to say, the most difficult gases to be catched because they're inert, so they don't react easily with components. Of course, xenon, for example, can be converted to different compounds of xenon, but it's quite, it's not simple operations for the purification of the gaseous streams, but to concentrate and to store these noble gases, different techniques were investigated. Here it is as an example for krypton 85. So it is cryogenic distillation, it is membrane separation, adsorption on coal, adsorption on zeolites, and combination of cryogenic capture and molecular adsorption, for example, with zeolites. So there are a list of different references. If you are interested, you can look for them. So, gaseous uranium hexafluoride that can be a part of gaseous streams in the fabrication plants or isotope separation plants. This compound can be captured using the columns with the sodium fluoride, and with this reaction, gaseous uranium hexafluoride can be converted to the solid complex salt of sodium and uranium hexafluoride. Iodine, one of, maybe it's not the hardest element to be captured, but it is one of the most dangerous, I would say, radionuclide when nuclear fuel is working in nuclear reactor. And among different elements that are produced in the spent nuclear fuel, one of the element is cesium, of course, and together with cesium iodide is can be very volatile. And there is different methods for localization of cesium iodide, and actually all of the known methods can be used. So it is just using of the scrubbers, using of the filters to catch the cesium iodide. So it easily react with water to form soluble salts, of course, and with the additional oxidation, iodide can be converted to iodine. If it is not a cesium iodide, but just an elemental iodide, there are a number of the methods. Here, 3 methods are listed to catch elemental iodine. So first of all, maybe the simplest one is the use of the alkaline solutions to catch the iodine. Iodine is disproportionating under these conditions to iodide and to iodate. But if there is a possibility of formation of the organic compounds of the iodine, for example, if there are some carbide fuel or some other material, carbon-containing materials, there is a chance to generate methyl iodide, for example, and with the use of the alkaline solution, metal iodide is not converted to the soluble compound, so you cannot catch the methyl iodide with this procedure. To make it more efficient, another process we proposed. First is Mercurex products process, where mercury nitrate and concentrated nitric acid are used to convert iodine to iodide and iodate, and methyl iodide also converted to the soluble compounds, to the soluble organic compounds. Iodox process is based on the use of very concentrated fuming nitric acid at elevated temperatures, and with the use of such concentrated nitric acid, it is possible to oxidize iodide even to iodide plus compound. So, and under these conditions, even methyl iodide is converted to the soluble compounds. For capturing iodide with the dry methods, different sorbents can be used. Many of them, it is just a modified, let's say, normal sorbents like charcoal or zeolites or silica gels that are modified with different metals or metal particles on the surface. For example, it can be activated carbons, so just normal activated carbon that is modified either with the iodine or metal iodides, because under these conditions, for example, with potassium iodide, molecular iodine is interacting to form potassium iode free compound, and thus molecular iodine can be captured on these sorbent materials. It can be activated carbons that are modified with the organic compounds. But we cannot use these materials at elevated temperatures, because these organic compounds can be volatile themselves. And the most efficient, I would say, it is the modification of the activated carbons with the silver, just a metallic silver or its compounds. They're very effective. I would say the most effective materials for catching the iodine, but they can be poisoned by different impurities, for example, sulfur-containing impurities in the gas streams. There are some other materials like anionides or polymeric sorbents, or even carbon fiber based sorbents to capture iodine. And other modified materials, inorganic materials like zeolites, silica gels, and oxides. And as you can see, many of them, they are modified again with the compounds that form, let's say, insoluble iodides when reacting with the molecular iodine. And again, the most efficient materials, they contain silver. One of the examples of these materials, it is silica gels containing different metals, including silver, nitrate, and just a metallic silver. And these two types of the silica gels, they were produced and developed in the Institute of Physical Chemistry and Electrochemistry of Russian Academy of Science. And these types of materials are supposed to be used in the industrial scale for the new reprocessing facilities, because the efficiency of the absorption of the iodine is very high. Even pure metal products can be used, but again covered with silver, copper, or zinc. But in this case, they are effective only for iodine removal, but natural materials, they are not really good for the catching of the iodine in both forms, in molecular form or organic form. So this different equipment, these wet scrubbers, cyclones, different filtering systems, they are used not solely, so it's not only one unit for the filtration or for the chemical separation of the radionuclides. Usually it's a combination of different equipments to remove big particles, to remove small particles, to remove radionuclides that can be chemically absorbed. This iodine, for example, if there are a lot of tritium content, then additional column, rectification column for the isotopic exchange. So depending on the process at your facility, there are different combination of different units. And of course, there is a control of the radionuclide content at the end of this purification system. Before these gases, all these gases, they are going to the environment, just to the air. So this ventilation system, they are not filtering and purifying the gaseous streams. They are also, of course, there is also a monitoring and controlling system for the discharge of these gaseous streams in the environment. And there is one example of the typical scheme at the first stage head operation of the reprocessing plant. So here you can see a dissolver. Yeah, so where spent nuclear fuel goes to the nitric acid. And then there is a system for the acid recombination. So it is vapor containing nitric acid. So different types of equipment used for the rectification of this acid. So it is a collection of the acid that can be either discharged or it can be purified and used again in the system. So there is a column for the removal of the iodine. Here it's caustic scrubber to catch iodine. Then there is additional columns to remove, for example, nitrogen oxide, so not just nitric acid, yeah, but nitric oxide, and different filters before the final discharge of this stream in the central system. Because every unit in the reprocessing plant at different stage in, for example, here is one of the typical scheme for the reprocessing spent nuclear fuel, where spent fuel assemblies are disassembled. Then there is a vol-oxidation step, then dissolution step, then separation, extraction, then fission product stabilization, and that goes to the repository. At every unit, at every stage, there is gas system, a ventilation system for each unit, and after each unit, gaseous streams, they goes to the central gaseous ventilation system, and there is just the blocks of the dissolver gaseous streams, for the cell streams, for the waste streams, and for the separation steps streams. So again, at every unit there is a certain purification system. After each unit, the gaseous streams goes to the central streams, and from this central stream, central unit, ventilation unit, the gas flow discharged in the atmosphere. There is another example of the purification system for the waste vitrification. So again, there is melting of the glass components together with the radioactive waste. All these components going from this feeding vessel where they mixed before. And then, so there is a high temperature and of course a flow of gas where first of all dust is collected. Then there is a condenser for the vapor. Then there is a jet scrubber, so like a maybe Venturi scrubber or tip, something like that. Then there is absorption of the nitrogen oxides, because here the initial components, they are nitrates. So there is a formation of nitrate oxide, the absorption with the pre-oxidation, and then you can see there is a collection of all these materials collected from these systems that goes back to this vessel, because all these components, they are components of the radioactive waste, and it goes again. But part of the gas streams, of course, goes through the system of the filtration systems, and finally goes outside. So very often when we are talking about the reprocessing techniques or immobilization of radioactive waste, we see the systems with our components like dissolution, then extraction, or vitrification, cementation, etc., etc. And very often we forget about the gaseous streams from this operation. But you can see that the treatment of these streams can be very difficult, and there are also a lot of different equipments, and there is, I would say, there is still a need in the development of new techniques, new equipment for more efficient separation and catching of the radionuclides in gaseous phase. For example, when the first gaseous treatment system for this pilot demonstration center was developed, there were something like 10 units for the purification of gas streams that included also aerosols removal, 2 units for the removal of the nitrogen oxides. Then there is additional unit for iodine removal, and some additional units. And it was tested, everything was fine, but the number of units make the whole system is very difficult to be operated, because if one unit is out of order, if it doesn't work, so you need to double all these systems, because if something will go wrong, you need to have a double equipment to not stop the whole process of the purification. And if you have 10 of the units, you need 10 additional units for the safety reasons. And later, I think in this year, it was a proposal to make only 3 units instead of 10. So because it was confirmed that 3 most efficient units from these 10 units can work at the same efficiency as all these 10 units. And it was done before, because it was known from the previous experience that all these units has their own efficiency, let's say, of the operation, and by calculation it was seen that they need 10 of these units. But when they checked later, after they already constructed this pilot gaseous line, and they checked that okay, it works, but it's too complicated. After they think more deeply, they finished with only 3 units. So and again, this gaseous treatment, me honestly, I saw not a lot of work on this system. Many people, they are more interested in, I don't know, extraction or solidification or other materials, but this part of the plant, of the reprocessing plant, or the radioactive plant, radioactive waste treatment plant, is also very important, because this gaseous flow will end up directly in the air, and it is very mobile phases. Yeah, so we need really a lot of developments in this field to make it more efficient and more efficient from also economic point of view. So I think that is all, yeah, from my side on this topic. So thank you for your attention. If you have any questions, you can ask, or we can discuss it in face to face. So I think that it is all for today, and you will have announcements, I think, in the group chat from Olga about the tomorrow tour in Kurchatov Institute. I hope everything will be fine.